as far as we are concerned, this is actually what you have in natural gas. These are the components, some of them. And you can see here, those are the pipeline specification in the US, where you have to lower your concentrations to this levels here before you can transport your methane. Of course, CO2 has to be below 2% and so on. And those stars here actually are for here in Saudi Arabia. We have wells that have high amounts of nitrogen and CO2. And we are actually working as we speak with Aramco to develop materials for these applications. But what's interesting, here in Saudi Arabia, we have actually the fourth largest reserve of methane, but we don't use it for things. We just burn it or send it to SABIC. So there is a golden opportunity here, at least to value, at least when it comes to the States, to value actually what you can use methane for. In addition to using it for vehicle application, also you can use it for an application other than storing it in a car, for example. You can also use it as a source of energy if you can remove all this in a cheap way. So that said, this is again my introduction. Just to give you an idea where are we going, we are interested in separating commodities and storing valuable energy vectors. To put it into perspective, this is actually zeolites, which are purely inorganic materials. They're very interesting, and actually they are very useful. You use them every day when you clean your clothes, for example, when they soften your water. And also, this is what makes the oil cheap for oil cracking, for example, like phosphate. But what's interesting here is the size of the pores is homogeneous. Means you have what we call isopores. All the pores are exactly the same size. However, you cannot change the metrics of those pores to adjust to whatever application you want. And also, they're very difficult to process when you want to make them as membranes. In other words, if you go to polymers, those are actually easy to cast. They're easy to process. However, you don't have this isopore thing. Means you have multiple size of pores. That means that you cannot use them efficiently for separation. For example, when you talk about nitrogen, methane, the biggest you can get is 2. So that means that we need better materials and suitable materials for this. And again, I might sound biased, but this is my pitch here. Here you have a material that has a hybrid character, where you have an inorganic component, an organic component. And what's interesting about these materials, as you will see down the road, that it allows you actually to control the metrics of this material as well as the functionality, as well as the surface of the pores. What are these materials? Again, this is something that summarizes what metal organic frameworks are. But as far as I'm concerned, being in this area for almost 20 years, the most important part about this area of chemistry that you can actually assemble these materials by design. If you don't appreciate the word design, means that you can direct their assembly to some extent. And most importantly, you can control the pore size from the Armstrong level, very small, to mesopore size at ease. And all the rest is just an output. If you can have this control, it means you can add all those things. And of course, this is not common in other materials. As I said earlier, the zeolites, you cannot do this. In our group, what we do, we tackle many things. Maybe I'll get to touch on a few things today. We're interested in storing and capturing carbon dioxide on board vehicles. Means you don't emit your CO2 out in the atmosphere. Then you can take it to a remote place. Then you can treat it. Of course, direct air capture. I'll show you an example. And of course, olefin paraffin separations, which are energy intensive, and methane storage for vehicle applications. So that said, I will not get a chance to talk about all this, but what's important is how do we make these materials? I used this slide maybe for the last 10 years. This slide shows two key things. Don't worry about the language here. The most important thing, that if you can actually have your building block to some extent, organic and inorganic, there is a way to know exactly what you're going to get at the end. So in this case here, what we have, those are our blueprint to make these materials. And what's interesting, just to make it in a very simplistic way, is if I take, for example, a cube and a square and link them with the same link, there is only a limited number of possibilities that can form. And in this case, it turns out that there is only 54 edge-transitive links. In other words, that have exactly one type of link. I delete this link, everything falls apart. So this is quite impressive when you think about tetrahedral, for example. If I take tetrahedral as a building block, I can make over 1,000 structures because there is too many of those. So here what we are adding is a control component that we can actually make our materials from our building block by design. I will not get a chance to talk about this structure here, But for example, here if you have truncated coboctahedron linked with a triangle, there is only one possibility. There is no other. This is called RHT. And this allows you to extend those structures to the limit of crystallography, for example, to get the structure. And this material here was actually used by Northwestern Group, where it holds the record when it comes to surface area, where they extended the organic link to that extent. So this is the blueprint. So meaning that if you can have a blueprint to target, you can actually use this. So now the question that you might ask, so what's the challenge? The challenge in metal organic framework, as of today, for the last 20 years, is how can you make these building blocks all the time in your solution? If you cannot make these building blocks all the time of solution, all what you are doing is just what we call shake and bake, hit and beat, and pray and wait. You are having no control. And most of the community today are taking advantage of this, but you can make these building blocks all the time. Then you can insert functionality. Like, for example, UI66 or zirconium compounds, the fact that this cluster existed and was discovered in 2005 allowed many groups to explore that. So that brings me to my next slide, which is, again, the most important part, is this inorganic component, which are formed in situ. So if you want to talk about design, you better find the right conditions to make these building blocks. Then after that, you can actually choose your organic link. Then you have certain structures that you can target. So here you have, for example, I just want to stress something that sometimes is confused. We call this molecular building blocks because they're molecular entities that do exist as discrete molecules, for example, and you can form them in situ. Then from here, you can choose the point of extension. In this case, we have the carbon that will extend to another building block. Then we define what we call secondary building units. That's a geometrical entity that actually directs the assembly. And again, you can see that you can have a myriad of building blocks for that. So that said, I don't have time to go into detail, but we developed many pathways and strategies to have this control over the assembly. I showed you the building block where you can target the simple structures, but also introduced what we call supramolecular building block, which are hierarchical building blocks that have more information, and in other words, highly connected building blocks that will allow you only to form one structure. The higher the connectivity, the limited the number of possible extended structures. And also, we introduced what we call a super layer building blocks, where you have now your layers are directing the assembly. In other words, if you have the ceiling and the floor, or what you need to change is the pillars, then you can introduce functionality. And this was not common in other solid state materials. And of course, we also can make what we call hybrid zeolite metal organic frameworks, where you can actually play with the exchange of cations. Here you have inorganic and organic, and those were the first materials that have this kind of topology, not only in their character, but also in their anionic character. And again, if you are interested, you can check these two reviews that have all the details about these approaches, and even many structures that do not exist are given in this review to be targeted. All right, that's said. So I don't know how I'm doing in time, but there is a long introduction. But just to give you, then after I will show you all how is this applied. Now coming to CO2, we heard a lot of people talking about CO2 capturing and separating. And just to give you an idea that every system is different. This shows you, for example, biogas, syngas, flue treatment, natural gas, confined space, and capture. Each of those, we need to remove the CO2, but each of them is different. It needs a different material. And here you can see existing materials that are used, and again, in this case, they're energy intensive. But most importantly, what I want to show you here is just we have bulk separation that's easier, purification. Then when you get to very low concentration, it's energy intensive and very expensive. When it comes to how we absorb these materials, this shows you the plot. For example, here you need 0.5 bar. Same processing is 10 bar. Flue gas is 0.15 bar. Then as far as you go, you will see that you are in the ppm range, for example. If you want to remove CO2 from confined space, you better have an isotherm that's this shape. Means that as soon as this material is here, your CO2, you just capture it. And that comes with this. So you need to have CO2 selectivity. Going from here to here, you have to have higher selectivity. Of course, you need to have, this is coordinated to absorption energetics. Here you want to have this material to absorb strongly, but also not as strong as chemically, so you can remove it by reducing your pressure. And most importantly, you need to have what we call uniformity of energy sites here. So you don't want to have only few sites that absorb your CO2, then after those are gone, then you will lose selectivity. So you need to have something that's continuously keeping this selectivity. In pictures, this is what we have. I don't need to go to this. There is many applications for capturing CO2 at low concentrations. In images is here, again, submarines, confined space, anesthesia. Of course, direct air capture, don't get your hopes high. That's very expensive. 1 ton of CO2 will cost $100 with existing technology. And we don't want people to believe that that's actually an exit road and emit CO2 as we do today. Okay, that said, that gives you an idea of what we have in mind. Now I will show you a list of results where we apply this to metal organic frameworks. First of all, this is a system just to show you that by using, for example, this kind of metal organic frameworks, we have a control over the pore size. First of all, we can just make 2 networks, one inside of each other. This is a metal, can be copper or zinc, SiF6, which is an inorganic hexafluoride silicon. Then this is bipyridine type ligand. You can see here that you can reduce the pore by interpenetration. Or you can use shorter linker with copper, for example, or you can change the metal, copper, zinc, and so on. Here I'll show you just by tweaking a little bit of chemistry, we make something that's very interesting properties. And I will not go into detail here, but just to give you the highlight of this work. So again, this is the sorption. I only limit it to 0.1 bar. You can see here one of the materials has a very steep uptake of CO2. And let's go into detail here. The first one, which is right here, has a 4.9 angstrom pore size, and most important, it has a steady adsorption heat. Then when we reduce this to pyrazine, you can see here, we enhance our adsorption to almost 50%, just by reducing the pore size by 1 angstrom. And this is all crystal structures. And you can see here, this material now is even one of the best materials for removing CO2 from natural gas, and this was published a year and a half ago. But what's interesting, by using this coordination chemistry approach, by going from zinc to copper, we can take advantage of the Yentler effect. We can have one set of the bonds that's shorter than the other one. We're hoping that we can reduce this even further. And sure enough, we can go from 3.9 to 3.5 and enhance even further this heat of adsorption. And again, we are talking about physisorption here. All these gases can come just by reducing the pressure, and it's done. And this material today is the benchmark for removing CO2 from the air. You just put this material outside and you just suck CO2 from there. And this is not done by EST, this is done by real experiments. You can check the papers. And the numbers here, for example, are given from breakthrough experiment as well as mixed gas adsorption. You can see CO2 nitrogen is one of the highest selectivity, which is almost around 2,000 selectivity. Why is this material unique? If you can, here you can see what you have is a periodic array of fluorine anions that they're sitting in a square that allows now CO2 to interact with 4 centers, and you have kind of a spillover that the first CO2 that absorbs go to the next one in the next and behind. Then it allows for the first time to have what we call thermodynamics and kinetic driven adsorption that allows for this material to be this highly selective. So we are trying to scale up this material, and it should be a good material to use for separation. We are not only putting our eggs in one basket. We try to have this also as a membrane or put into a mixed matrix. I'll give you just a highlight. We made the membrane of this material, for example, here. This is not published, and this can actually be continuous. You can have a selectivity of CO2 over hydrogen of 35. Normally, if you do single gas, hydrogen will diffuse faster. It's smaller, but in this case, this material is highly selective for CO2. We can also make membranes with anionic metal organic framework. Then we can exchange the cation and tune the properties. For example, by having dimethyl ammonium, we can have this material to diffuse CO2 faster due to favorable solubility. Not only we are interested in membranes, we are as continuous and pure MOFs, we are also interested to disperse those into polymeric support. So in order to do so, you have also to control the geometry of those metal organic frameworks and their shape. And this is just an example here where we can go from a cube to truncated cuboctahedron and have exactly homogeneous things. And if you use emulsion, you can make even colloidal structures. So again here, with all this, it shows that we are interested in a sorbent as a bulk material, as well as a membrane, as a pure MOF, and also as mixed matrix membranes. So now let's go to the design part and show you how much control we have about these materials and show you a few examples So this is an old system. We discovered this indium hexacarboxylate here. And this material normally forms when you have carboxylate at 120 degree. So if you look at this here, you have trigonal prism, again the point of extension linked. Then if you take this with the square, we know from our 56 expected structures, which is called H-transitive, that you can make this structure. This is exactly what we did. So we linked those benzene dicarboxylic acid with azo group, and we expect to get this structure, and that's what we got. And at that time, this was a targeted structure that we can have confined space, high localized charge for hydrogen for the DOE project. But what I want you to keep in mind, that this cluster exists with many metals, but we were targeting aluminum for the last 8 years to make expanded structure, and I'll show you one example that if you keep insisting, you can find again the right conditions to make this cluster. In theory, we know we can make it with aluminum, but it's very difficult to make this type of cluster unless you find the right conditions. So let's look at this material very quickly. It used to be one of the materials that have high density of hydrogen inside the pores, and it has very high moderate hydrostatic heat, but again, homogeneous means all the sites are equivalent. Then again, if you are interested in hydrogen, you better have a material that have very high surface area, very small, pore size around 1 nanometer, and high localized charge. And you can sense that the two are correlated. If you make large pores, you lose surface area and so on. So here I will go quickly, so we can tune this platform. As soon as you have the conditions, we can make this, for example, put chloride anions into the channels. We enhance the electrostatics, or we can put iron. This is not published, but just to show you by changing a little bit, you change completely the properties of this material. Okay. So here I want to show you something that, again, when you have this, an example that just published recently, when you have these building blocks, reaction condition fixed, now you can play with your ligand. So this is an example here that again I just showed you that we can use this trimer with indium. We can make this material that's good for separation and storage. But what we're interested in is aluminum trimer. If you're interested in direction, you can go here. But we use this extended ligand because we want to have large surface area, small pores, and actually, in this case, the pores have to allow for 2 molecules of methane to be adsorbed. So we make this material for the first time using aluminum trimer and this ligand. And this material has very high surface area, around 6,000 square meters per gram. But I forgot to mention that this material has channels, which are here, and has also cavities. But going fast here, I will show you that this material has very interesting properties. From topological perspective, again, just to show you in this case, that you can look at this ligand as 2 triangles linked together. So meaning you can actually design your moieties. Then of course, this is, by the way, it's called EduCure. It's EduCure because this topology was discovered by us the first time in 2007. So as soon as you find the conditions to make those building blocks, you can change your organic linker. It doesn't become a problem. So we're exploring now if you make these channels more hydrophobic and so on, what is the impact on absorption properties. But what's interesting, this material is porous and crystalline. You can see here the surface area. I think my computer is not responding quickly, but let's go fast here. So again, they're all highly porous. Those materials, for example, they don't need to use supercritical C2, just quick exchange. You get completely the ultimate absorption. We always check our material stability. As you can see here, we do our activation, then after we do sorption, and we do powder X-ray diffraction at 400 degrees C, for example, you still have the same surface area. So they're quite stable. But what's important here is that this material has one of the highest methane storage capacity. Without going in detail, again, you can check this. We are surpassing the 700 cubic centimeters per gram STP, or even 0.5 gram per gram. And again, it's at low temperature, but here the concept is that this material allows you to store large amount of methane. And most importantly, at the opposite of other materials, when you lower your temperature, you are actually increasing the working capacity of this material due to weak interactions of methane at the surface at low loading below 5 bar. So quickly here, just how this stands without going in detail. So this material has the trade-off between volumetric and gravimetric. And we did also simulation studies where we changed our organic link, and you can see here that this material actually is better for methane. So without going there, but just what I want to show here, that when you find how to make your inorganic building block, now you can play with the organic to control the pore size, surface area, and so on, and have very interesting properties. So not only it's good for methane, it's also for other gases. For example, here you can see, I have no idea what this is slow, but anyway, this is in comparison, for example, one of the best materials in A125 by Professor Farha that shows very good oxygen storage. Also, this material has one of the highest now capacity for storing CO2. At 35 bar, for example, you can have 2 grams of CO2 stored in 1 gram of the material. And also, this has very high storage absorption at low temperature, but that's not important. So let's see. So I've been talking for 24 minutes. Okay. So again, when I talk about doing these building blocks, half of my group always works to discover new building blocks and reaction conditions to have this building block. So in other words, you can think about it as serendipity leading to design. When we find those building blocks, now we can explore them to make structure. This is one example where we introduced the polarized ligand that has tetrazoles and carboxylate and fluorine groups to have this polarized ligand so we can enhance the interaction with CO2. We explored with many metals. That allows us to discover this cluster here that has hexanuclear lanthanides and bridged by 12 ligands. But what's interesting is this gives you this building unit that's 12 connected and the linear link. So again, it's a platform that's here that can allow you to change organic and inorganic. It has octahedral cages and tetrahedral cages, and you can make it with almost every lanthanide, as well as you can change the organic functionality. So again, here, I'll show you one example. This allows you to control the functionality and the pore size. And since time will not allow, we'll go fast. So this material, for example, I think my computer is not in synergy with the projector. So this material has these cones and has this polarized charge around. It allows CO2 to absorb very strongly, for example, but still physisorption. 60 kilojoules per mole means that if you have ppms of CO2, it will be absorbed. But again, this material has very low amount of sites. So as soon as the sites are saturated, everything decays. So again, here, what we have is this kind of cones that have fluorine, tetrazoles, and lanthanides that create this localized charge density that enhance the CO2 absorption. This material is good to separate CO2, for example, from nitrogen, as you can see here. This is proven by adsorption and breakthrough experiments. But what's important about this material, without going into detail, this is one of the materials that we are working on with Aramco because it has very high stability. It's a thermal stability. You can boil this in water, no problem, it stays. And you can even expose it to H2S, and it's still stable. And this is, for example, this material, we're using it to remove CO2 and H2S from natural gas in coordination with Aramco. But what I want to point here, when you have a platform, we talk about design, meaning that now you can actually change the properties of your ligand for a given application. This is an example here that shows, for example, instead of using the benzene here, we use naphthalene because we want to reduce the opening and access to these channels. And you can see here this is all the benzene ring in equilibrium, the naphthalene. So the pore size is getting smaller. So again, this material, this is the sorption. But what's interesting here, you can see the absorption of isobutane, for example, here, is slower than the absorption of butane. It means that you have kinetic separation between these two, and this is actually proven by breakthrough experiment as well. So again, having this control of the window of the pore allows you to control the sorption properties. We can do that in films as well. We can grow films. Then we can actually take the same advantage. The larger molecule will diffuse slower. But I want to show you something, so I want to get time on that. So you can think about now that we can have this triangle. We can reduce it even further, right? So before I get to that, this material is stable, and you can boil it in acid and sodium hydroxide. It turns out that the shorter your linker, the compact it is. In coordination with the cluster, you enhance the stability. And of course, this is confirmed by the sorption. So let me just put to perspective what I said. We made this structure. We know how to make this cluster all the time. We need to have fluorobenzoic acid or fluorinated ligand. Then now, every carboxylate you can make the structure with. And this link here, you have a triangle like this, and you can sense that this triangle has a large pore behind. If I reduce the linker, means I can still reduce my pore as much as I want. If you have normally a cube or a hexagon, you cannot do that. So by reducing this, means they can discriminate between my molecules. So the idea is to reduce even further to separate molecules that are of importance. So again here, just to summarize, you can control the width of your triangle. You have what's called kinetic diffusion of molecules, meaning molecule can go in slower and faster. But if we reduce this further, we put, for example, fumaric acid, we reduce the pore size to this size. And here, this is the first time that you can see this in a porous material. What we have now is a control how molecules can diffuse. And interesting enough, this material is stable in water, chemically, and so on. But here, for example, if you take branched paraffins, they don't adsorb at all. But if you take, for example, butane, it adsorbs. So here we have, for the first time, what we call molecular exclusion for real. And this is confirmed by adsorption, calorimetry studies, as you can see here. This is isobutane adsorbing. This, it doesn't adsorb. So here we have, for the first time, molecular exclusion. And we took this principle, by the way, I cannot talk about that, and apply it to propane, propylene, and we can do exactly the same thing. So we have molecular exclusion, and this is actually highlighted in many news media. All right, so I will take five minutes to close. So when we make these building blocks, we can design. Now I'll show you that we are not limited only to existing building. We use our knowledge of topology and chemistry to discover new building blocks. So here, for example, we know that if you take rare earth metals and this triangular ligand, it's not compatible with the building block I showed you earlier that has 12 connected nodes. Okay? So again, if I take rare earth, benzene, fluorobenzoic acid, I can make this hexanuclear cluster without a problem. And this was proven crystallographically. Take this DMF, I can make this cluster. However, if I take this and this and this, you get only this if you don't have fluorobenzoic acid. So that means that here I have a room to discover structures that don't exist. So this and this are not compatible. So meaning that I can discover new structures. So I'll go first here, building block, fluorobenzoic acid. You make this cluster. I showed you FCU. If you take it with the square, we make FTW. This is very easy to make. So you can make this structure here. But if you take this with the triangle, they're not compatible. We have now a cluster that evolves to make a cluster that can accommodate this triangle. So you can see here that topology and chemistry work alongside. So here we make a structure for the first time. It's called Guilherme. What you have here is an evolution of the cluster. It goes from hexanuclear cluster to a non-nuclear cluster. This is the mechanism. Again, if you're interested, you can check the paper. So since this 12 connected is not compatible with triangle, 3 more metals came in to expand this carboxylate to be 18 connected now. And you make this kind of highly connected building block. Triangles with 18 connected, you make this new topology. And it's highly porous. Then I will skip all this to show you how we can use this again. You do the PXRD, sorption, high porosity, and so on. And this material has some interesting catalytic properties as well as sorption properties. But I want to get to the point that, again, separation, you can take actually synthesis of cyclocarbonate. But if you are interested in details, you can go here. But what does this mean? What I want to share with you, without spending all my lecture talking about carbon capture separation and these 2 papers at the beginning, I want to emphasize that this chemistry metal organic frameworks allows you to control the assembly of building block into a given solid state material. So here, we discovered this building block. Again, always people say, oh, Mohammed, you made this structure. Then after you went back and look at the topology, there is a design. This structure did not exist at all. It was made at KAUST. Then now we have this building block and this. So we want to now use our approach of super building block to implement that we can use this topology as design. So if you look at this and this, they're the same. But let me define for you what is the super building block approach. The super building block approach was inspired in the fact that here I have 24 connected nodes, means that this is connected to triangles, and each triangle is connected to 24. If you look at your coordination chemistry, it's very difficult to have a cluster that has 24 peripheral carboxylates. Almost there is none. So we didn't wait for that. We said, you know what? We need to find how we expose these 24 carboxylates outside without spending so much time to find this cluster. We're still looking today, and we don't have that cluster. So normally when you have your network, what you do is you augment the vertices, means you look at the geometry of your vertex figure. Like here you can see that this node should have this geometry and shape, and this should have this shape. If you have those two shapes, you link them together, and Omar Farha can witness that, you always get this structure. Unless you do something where you have flexible ligand, then you get layers. But generally speaking, you get this structure. So how do we get this? The idea is we know how to make copper paddle wheel. We use benzene dicarboxylates. We made this in 2001. Then now if you look at it, you can expose those here. As you can see, if I can go back. I don't know. But anyway, the fifth position of the BDC is sitting exactly in this position. So what we did, we just put tetrazole here, or another benzene that's triconnected, then you make exactly this structure. And this is a very powerful approach. Then, of course, you can make, I'm sorry about this, but that's part of life. Anyway, so we can make those RHT type of maps. Then you can exchange the organic and extend them. So now, can we apply this approach to the topology that was discovered? And I think, even if you don't care about this chemistry, you will appreciate how discovering this topology, then you can actually take it and export it to other chemistry. So let me take you quickly through that. So what we need is a building block that resembles this. And this is, we call this supramolecular building block. Again, it has copper paddle wheels bridged by bidentate and ditopic ligands. And this exists. So if you look at this and look at its peripheral nitrogens, they're exactly the same as this. So all I need to do is to position this here with a triangle. So let's look. You have two sets of 120-degree angles, one set of 90-degree angles, and the copper paddle wheel. So if I have a ligand that has 2 times this and 1 time this, and I can now make this all the time, and that's the only possible structure to form between 318, I should be able to make this structure without a problem. So going through very tough organic synthesis with multiple steps, if this can work. So we're trying to make that ligand that has 2 120, 190, as you can see, multiple step synthesis. If we realize normally to have 2 120-degree angles and 90, we should be able to make that structure, and that's sure enough. We get exactly the same structure, and this one was designed after this one was discovered. Then you can see here, this is the altered version of this. Now we create even more space inside this. So I think this is design. And you can ask, why is it design? I'll tell you exactly one thing. So again, this was highlighted in Nature Chemistry, and they have it as a cover. They appreciate that. But let's look at the two structures. This is the 318 that has only 2 types of edges, means that the links between your inorganic belong to 2 types. If you wanted to design that structure with copper paddle wheel, it will be almost impossible, because you have 5 types of building blocks, 5 edges, and faces, and tiles. So we managed to have this structure because we discovered this. And this was designed. So again, here, the whole idea is metal-organic frameworks offer potential to play between structure and properties and add function to them. So let me close here, just to tell you, for example, that this is not easy, and many people in math community take advantage of this. So again, we discovered this, right? Just to make it doesn't look like simple. Okay. We have this structure. This is we discovered we use this. We know if I make this building block, I can make this. But guess what? This building block is not easy to make. And the only difference is those here are eclipsed and those are staggered. Same building block. Make this building block, you're going to get this. But there is no building block that has this geometry. So again, when we talk about metal organic frameworks, I think everything goes together. It's not those people mixing things, it's more having this control of the structure that you have at the end. Then you can correlate the properties, as Mustafa Sayed said in his opening planner lecture, that properties and structures are directly correlated. So again, if you know how to make this Omar, feel free. This is a very nice structure, by the way. And it's hexagonal, has one-dimensional channel. All right, so I'll skip all this. This shows that if you have high connectivity, you have limited number. I will go through all this very quickly. It's not important. Then I will close because I think I took so much time. So again, since we have this building block, we can change it. And this is an example. By changing the symmetry of the ligand, we can have this kind of versatility. We make new structures. And one important thing, again, to make you appreciate this building block thing, and I'm not sure many people in the math community appreciate that much, is, for example, double-6 membrane is one of the most important building blocks in zeolites. There is no cluster as of until recently that has this. So we were aiming to find that, and we did, but we got scoped to some extent. But if you have this double-6 membrane, there is so many structures you can form. But here, this allows us to find this cluster for the first time with lanthanides. And double-6 membrane, we know exactly what we're going to assemble it with, and some interesting structures. So again, let me just show you here. So we have this versatility. You have these clusters. They have either 6 lanthanides, 9 lanthanides, but they have different geometries of carboxylates. One example here, we have this mononuclear cluster that has trigonal prism. Then I will close here. If you take this cluster, for example, and you link it with a square, we know exactly what we're going to get. And we've been chasing this cluster for almost 15 years to make this type of shapes. But when you have this handy in your hand, you can make structures. So here you can make this structure. And we made that maybe a year and a half ago. But Honkaizo published one with zirconium, but not mononuclear cluster. Then you have this periodic array of porphyrins. But now I will close here by showing just the video. And I know it took so much time. I apologize. But again, this is just to share with you this. So normally, if you want to make layers, as I said, cylinder on the floor, there is 2 ways to link squares, either square grid or Kagome. If you can make those layers all the time, you can change the metrics. Then I will put the video to show that. Then I apologize if I took so much time. Yes, I am 3 minutes over. So if you look at this structure, this is HCOST. It has square paddle wheels, but it actually has layers that are pillared by quadrangle. I'll show you this approach where it takes us here. And if this video works, this shows a structure and how when you can make the layers, you can change the pillar. We call this, again, super building layer. And this actually approach, the patent or the concept is held by USF and KAUST. So if you look at this structure here, you can look at it as a 3-dimensional structure, or you can look at it as built from layers. And this layer is the most common possible structure to form by assembling squares. We call that square grid. Means if I take squares with linear, I will make this structure. Then if you look even further, you will see that these layers are just linked with another square, which in the HCOST is a copper paddle wheel. So now if we can make an organic link that actually can position this BDC in the same place, we should make exactly the same structure. And sure enough, that's exactly what happened. You will see here that by using benzene and epoxy group, we make exactly the same structure. So now, if what I said is true, I can put an extra benzene dicarboxylates in here, and I should get exactly the same structure. And that's exactly what happened. We have 3 carboxylates aligned in the channel. They don't interact with the coordination whatsoever. And this is actually was not taken by the community because it was hidden in the paper. But you have 3 carboxylates in the channel. Then if you have carboxylates, you can use it for separation. You don't have carboxylate, you can use it for storage. Then you can expand this as far as you want. As you can see here, again, those are all crystal structures. They're not cartoons. We can expand our linker and make exactly the same structure. And again, this is very nice because this material allows you to have the same structure, same properties, change the metrics, and change the functionality. I think with that, I will thank the people that did the work. I will stop this video here. This is my group at KAUST. I would like to thank KAUST funds, of course, UNICEF, Aramco, and so on. And thank you for your attention.
Thank you, Professor Dawoodi, for your interesting lecture. Now the floor is open for just a few questions because we are out of time.
Very nice. Learned a lot.
Maybe you can give him the microphone if the people at the other side are listening.
Thank you very much. Very nice. I learned a lot. So you seem to suggest that this design is basically on the basis of topology. I was wondering the role of thermodynamics and kinetics in making these things. You know, do kinetics limit sometimes making this?
I mean, you have the kinetic problem, most importantly when you have multiple structures to form.
Yes. Oh,
Topologically already, like if you take tetrahedral, there is too many structures to form.
Yeah.
Then that's why the zeolite field changed before by using structure directing agent to favor one over the other one. Here we still have the same thing. If you take tetrahedral, straight linker, you make a diamond structure, that's the most easy structure to form. But if you add other things, there's many possibilities. But here the idea is to have one structure that's actually topologically possible. It means the building blocks, put them together in order to make there is no other possibilities. If you take, for example, this truncated cubooctagon triangle, there is no other way to make a 3D. Here we are talking about, keep in mind, we are talking about same linker. If I take, for example, a longer linker, a smaller one, or I take this room, I have small tiles, large tiles, I can do many patterns. But here, fixing the same distance, you get only one structure.
What about thermodynamics then? You know, kinetics-wise, or topologically, it's only one possibility. But will thermodynamics always allow that in energetics? That is.
Yeah. Okay. If you have the right, yeah. But if you have tetrahedral, for example, you have both, not only the thermodynamic kinetic. The most thermodynamic structure for assembly for tetrahedral building unit, unless you don't have charge, will be the diamond structure, because that's the most easy to form. But if you have angles changed and you have templates, you will make other structures. That's why zeolites, it's very difficult to make other structures, because you get always the most thermodynamic stable one, and they're very small kinetic differences.
Any other question?
From the ladies?
From the ladies?
If there is any ladies. Omar, you have a question? You look at
No question.
Please.
He has a question.
Okay, from the lady?
They said no question.
We are out of time. Sorry for that. From the lady section, please. Go ahead.
He said no question.
No question?
Yeah.
Okay.
I wasn't here in the beginning, but as far as I know,
Yep.
this material you cannot functionalize. So only you are using it for adsorption.
What is mean functional?
What chemistry you can do with this material, except the adsorption.
What do you mean by functionalize?
Functionalizing it, you can go farther to do a chemistry with this material.
We are doing chemistry. We're doing
What
catalysis.
chemistry? I didn't see that.
We're doing catalysis. We're doing
This
is not chemistry? It's not chemistry?
No chemistry,
No,
but only you have adsorption.
It's okay. I'm following you. Go in detail. What do you mean?
How many ligands you can use in this material? How many?
Go one further. What do you have in mind? You can speak up. Go ahead.
We can speak. What
Yeah.
chemistry you can do with this
What do you
material?
mean by chemistry?
Chemistry, farther you go with this material.
What does that mean?
You can do reaction.
Like what reaction?
You add a new material and to this block or cluster you are making it.
Those are extended solids, okay?
I know that.
So
I
what do you mean by
At
functionality?
MSU
We take this materials, we make membranes, and we separate. We
What
take those,
kind-
then we can go golden side and outside. So what do you mean by chemistry?
What kind of membrane you are making it?
It's okay.
What do you mean, what kind of membrane?
Where you can use this membrane, brother?
Dr. Aram.
What does that mean?
Give me an example.
Are you talking about industrial applications?
Yes.
This problem, I have it since 97, but you will see, it will go out there soon. And those guys are making that. But you have to be patient. But you should appreciate the lot of, listen. You should appreciate the lot of chemistry that's going here in 15 years. We came further away. If you talk about zeolites, 1960, they just started. It took them 50 years to have industrial application. Mesoporous materials discovered in 1991 by Chris Gay. Today, there is no application. Thank you very
Thank
much.
you, Professor Nafadi. Let's say thank you for him. Sorry for that. Professor Ayman, please.
If you follow the field
Please,
correctly, you'll
please,
see
please.
there is a lot more chemistry.
بس كده تمام. بسم الله الرحمن الرحيم. Let me start. First of all, I want to say that for an electrochemist, we cannot compete with synthetic and inorganic chemists in making things. But what we're trying to do is we're trying to improve the picture, getting something that we can study, not only the chemistry, but also the application of the materials. So what I'm going to talk to you today is about some simple approaches that we can use to make micro and nanostructure of the metal TCNQ. And this is some of the university I'm associated with, and currently I'm part of KSU. So outline of my talk, I'll give you a little bit of introduction about this metal TCNQ, and then how we make it chemically and the obstacles in making these, and then the electrochemical and photochemical approaches that we developed. Basically, TCNQ is an organic molecule. It's an electron acceptor that can be reduced by one electron to give a highly stable radical anion, which can be also further reduced by another electron to give you the dianion. And a lot of inorganic chemists, they use either the monoanion or dianion to create a new and lovely structures, as we've seen with Dr. Al-Dawdi talk. Simply for us as electrochemists, what we're trying to do is we take a solution of TCNQ and acetonitrile, for example, and then we're adding another electron to it, so we can form the TCNQ minus, which is the monoanion. Now, the work in this area is really driven by a lot of application that you can see now, starting from memory and energy devices, organic light emitting diodes, and so on. So the interesting experiment that it has been published in this area, where we can make that what they call it organic metal. And normally this is when you have an insulating material, which is a TTF, tetrathiafulvalene, and then you have a TCNQ and other insulating chemicals. However, even in the crystalline solid, when you try to get these in contact, they interface between them, they actually become superconductor. And this is generate a lot of application, like the conductive self-healing materials and so on. Now, you can use any metal in the periodic table to make such materials. All you need is to generate the TCNQ monoanion, and then you can react it with a variety of metal cation, depending on the application and what you want to use it for. One of the historic examples in this material is the copper TCNQ, and actually the interest in this material comes from the fact that it undergoes a switching property, which means it can undergo, or it can go from insulating to conducting phase as a result of inducing that with light or electricity. So the simple way of making this material is just trying to react TCNQ, which is the tetrathianoquinodiamethane, with a copper iodide. Then you can make this copper TCNQ. You can get morphology like this. Another way of making this is through spontaneous electrolysis, and this is by taking a copper sheet and then trying to vapor deposit TCNQ on the surface. Then you can make the copper TCNQ in different morphologies and in different applications. From electrochemistry point of view, because the majority here maybe they even don't know how we can run this kind of experiment. So this is a simple instrument that everyone can buy and can use. And this is our electrochemical cell with 3 types of electrode. And then this is when you look at the structure of the electrochemical cell. So normally, we have a reference electrode, we have a counter electrode, and this is a working electrode. It could be from different materials. And then our sensing or how we do the experiment, it depends on the type of electrode that we use. Simply what we do is we just scanning, we applying a potential through this potentiostat to the cell, which would contain at this time, if you have a copper, we would have, let's say, copper sulfate solution. And as we apply the potential, we get to a point where we can reduce TCnQ by 1 electron to make TCnQ minus. And now it's in the solid phase. And as a result of forming TCnQ minus, then for a charge neutralization, copper has to actually migrate from the solution into the crystal lattice to form copper TCnQ. When you oxidize back, actually what happened is you oxidizing TCnQ minus to TCnQ, and then copper has to release to the solution. However, when you cycle this for many times, you can see that this one is going down and this one is going up, which means from the physical property of the material that this copper TCnQ actually exists in two different phases, and they have two different morphology. One of them is highly conducting and the other one is insulating. This is what we can gain from our electrochemistry background. Until the time of Zubair, where he started to develop this ultra-fast electron microscope, and he started to look at the crystals of copper TCnQ to resolve the mystery of that. So he showed that when you have the normal crystal of copper TCnQ under high magnification of the ultra-fast electron microscope, they found there is a cracks in the crystal. Along the whole crystal, there is a cracks. And this is probably around 10 angstrom. And that cracks actually making the crystal is insulating. So that's why when you have two electrodes in there, it doesn't conduct any electricity. However, when you actually apply a light, like you irradiate with light, then the crystal expand. And as a result of that, you can see that the crystal start to become, continuous crystals. So all of these gaps are now filled, and therefore it becomes conducting, and so on. So based on and off, which is applying light or not, then you can see the cracks coming back, and that explains why we would have this kind of different. One phase is conducting and the other one is insulating. Now, getting back to the metal TCnQ, there is a long history here how to make this material from a synthetic point of view. And a lot of efforts, different methodologies has been applied to make this material and then to characterize it. However, if you look here are the obstacles or the problems of this material, they are coordination polymers. And therefore, you cannot really recrystallize or make it in a pure form. And that always make this material hard to grow single crystals out of it. What you can get when it is in the best form is this kind of shapes, which is really not defined shapes or not defined crystals. And therefore, for us as electrochemists, we find finally an angle to get in, and then we can use our techniques to develop a methodology where we can make at least a better crystalline shape or control the morphology of these materials. So what we did is we developed with Professor Alan Bond in Australia 3 different approaches that we can use to compete the inorganic chemist, and we say we can do a better way of making these materials. So one called, we know about the crystallization, but we use the electrochemistry to make electrocrystallization, and of course we use that in organic solvents. Sometimes we can do this chemistry in the solid phase. We do not have even to go to the solution phase, so we do this through solid-solid transformation, and the photocrystallization again from organic solvent and ionic liquids. So one of the early work that we did before is, this is cobalt TCnQ, where we can use our techniques to manipulate the structure, and we can get either these long tubes, or we can get a crystalline thin film. So again, this is very much in details, but what I'm going to show you is when you have a solution of TCnQ, apply a potential through this instrument, you can get what they call a cyclic voltammogram, which is showing 2 reversible processes. and that indicates that the monoanion and the dianion that you're forming are stable, at least on the CV time scale. However, when you add any metal cation like cobalt, nickel, and so on, you can see there is a massive change in the voltammogram. So the black one is now going to the blue one. So that actually sharp increase in current is consistent with that we deposit a new material at the electrode surface, and this material is basically the cobalt TCNQ that we're forming. So the mechanism is very simple. So you have, if you say 2 molecules of TCNQ taking 2 electrons through a reduction process, we're forming the TCNQ minus. In the presence of any metal cation at this point is cobalt, we're forming cobalt TCNQ. This is at the applied potential from 0.1 to 0. However, if you increase the potential a bit more, there is a chance to form that kind of intermediate, which can also be giving you the final product as the same thing. However, the morphology of the two are different. So this is a typical design. So this is our cell, 3 electrodes. That's a working electrode. And this is a camera. We're trying to see if we can monitor the formation of cobalt TCNQ in real time. So if you apply a potential, which is 0.1, and then you can see we reduce TCNQ now to TCNQ minus, which is a green color. In the presence of cobalt, you're forming the cobalt TCNQ. I have a video here. I'm not sure if it works. If it does work. No. Anyway, so this is typical what you can get. So if you have a simple experiment, 1 millimolar cobalt and 2 millimolar TCNQ in the presence of acetonitrile with this supporting electrolyte, you're applying at that deposition potential, then you can form these kind of needle-shaped microstructures of the cobalt TCNQ. And the real time of this is around 3 minutes. So you can make this material in a 3-minute time. However, if you apply a different potential, not this one, the most negative one, which is minus 0.1, then you can get a different morphology than what you can see here. If you can see this hexagonal shape are not fully filled with the material, not the building up. So if you leave it for a long time in the electrolysis cell, you can have this crystalline film. Interestingly, although this counter anion, it doesn't really participate in the chemistry. However, it does affect the morphology of the material, and that's what you can get at this point. So we're getting different kind of morphology depending on the counter anion that you use for the cobalt salt. We developed actually an electrochemical cell where we can monitoring the deposition of the cobalt TCNQ material, as well as measuring the XRD in situ using the synchrotron radiation. And at that time, we didn't have the synchrotron in Australia, so we used to go to Japan in Tsukuba synchrotron to make these kind of measurements. The reason why we use the synchrotron, because this material is really tiny crystals and hard for a normal spectrometer to get it. The second approach, which is very simple, we can do a lot of work on this. So basically, we start with TCNQ. We just modify any glass conductive substrate like indium tin oxide by the solid of TCNQ, we're getting this amorphous structure. You can also get the TCNQ dissolved in acetonitrile and drop cast it to the electrode surface. You're getting this kind of morphology, as well as if you start with spin coating. So spin coating, you can get different types of starting material. Now, we take this electrode, dip it into the same cell containing a solution of cobalt, for example, at this point. We get a different type of voltammogram here, but what I'm showing you is a solid state voltammogram. That means we're not in solution phase anymore. We are in solid state. And what we do is actually, again, reducing TCNQ to minus, then followed by incorporation of the metal cation, which is cobalt, into the crystal lattice in here. So this, you can say this step is a formation of cobalt TCNQ, and this back one is an oxidation or decomposition of the material. Now, you can see what we did here is we're taking that electrode, which is only TCNQ as a solid, in a substrate of indium tin oxide, put it in that electrochemical cell that contains only 0.1 molar of cobalt nitrate, for example, and then doing cyclic voltammetry for 40.5 cycles. And you can see that we're going from this to this through the solid state. So this is basically a cobalt TCNQ material, and they have some twisting structures and features. An interesting one here is, instead of applying cycling potential, what we do is depositing potential. So what we do is we're holding the potential at this value for 10 minutes, and then we take the electrode out and trying to look at it under the electron microscope. So you can see now that this amorphous material is giving us this kind of pattern where we have this kind of nano or microstructures and all having outgrowth from the crystal. We did also an interesting experiment. This is a drop-casted TCNQ. We dip it into a solution of cobalt. We reduce this by 1 electron for this applied potential for 10 minutes. We can see now that the whole crystal is still intact. However, it is fully covered with the features of cobalt TCNQ. Why it's grow like this? Because of the semiconducting nature of the material. So if you start to focus more, you can see that these are wires of cobalt TCNQ that we're making. This raises the question about where is the initial nucleation and growth happening. And we start to look at the bottom of the crystal, which is directly in contact with the electrode surface. And we found that this triple phase junction is the one responsible for making this material through nucleation and growth approach. Mechanism is very simple. You take TCNQ by 1 electron, you form the minus. That's in the solid state. And then you add the cobalt to this. Then you form the cobalt TCNQ. However, if you want to oxidize this back by removing 2 electrons, you get back a solid TCNQ and cobalt can be released to the solution. A curiosity-driven a phenomena for any chemist, he would say, what would happen if you change the nature of the metal? So what we did here is we go for manganese, iron, and nickel. You can see the voltammetry is very much same. However, we have a different values for the delta EB. And this is a kinetic parameter, which means that the precipitation or the formation of these materials is metal dependent. One of the interesting features that when we change the cobalt to nickel, we get this kind of morphology where we can get a flower-like morphology. And here I'm going to just summarize how we make this. This is what we can get from the electrochemistry and identify what a process we have. And then this is kind of structures that we can generate from this simple TCNQ crystal, the formation of nickel TCNQ. And you can compare it with the cobalt. You would say it is shorter. The crystals are shorter compared to the cobalt. Now, how we make this flower-like? So we just dip this kind of electrode into solution of nickel, applying a potential. And this is, we cycle that potential for 15.5. You're getting this kind of features. When you start to look at it under a higher magnification, you can see it is flower-like structures. Then another question, what would happen if you have a mixture of cobalt and nickel into the same solution? Which one would compete at this point in intercalation with the TCNQ minus? And definitely this is for the nickel and this for the cobalt. So from a kinetic point of view, nickel is going first and then cobalt later. However, when you give it more time, the thermodynamic would prevail and cobalt would be the dominating species into the crystal lattice. And this is the difference in crystals between the cobalt and nickel, as you can see. You can extend this to iron, for example, and you can get bundles at this point of iron TCNQ. This is the electrochemistry of these materials. And again, you can get actually this kind of engineered, I would say, crystal structures of the iron TCNQ, where you have some of them, they having outgrowth from the crystal. The remaining bit is just, having multi-dimension growth. And nature of this coming from the fact that it is semiconductor, so it can grow in different dimensions with no problems. Then you can just modify this again in the presence of iron. You can get this kind of bundles of iron TCNQ material. In the manganese case, however, it's a bit different from the copper. This is a phase change. However, in the manganese, although the voltammetry look like very much the same, but what we have is just a kind of morphology change. So we have only one phase, but a changing morphology with time. So how we monitor this? Actually, we start with electrode like this. We put it into 0.1 molar of manganese. We apply a potential. We get this kind of fibrous material of manganese TCNQ network. When you cycle this for about 5 cycles, you can see that some of them start to be growing big at the expense of the fibrous material. When you give it more time, you can get the same material in highly resolved. So this is, again, you can get this kind of different morphology of these materials. And one of those is interesting system is the zinc, actually. And zinc has an application that you can get into 2 different morphology and 2 different phases. The zinc material we can use as actually moisture sensors. So because actually what happens is if you have a zinc sheet in the presence of TCNQ and acetonitrile, no reaction. However, when you start to adding a drop of water, then the reaction happens suddenly with a blue color change. And this is because of formation of zinc TCNQ with H2O. So this is why we can use this as water or moisture sensors. Just to summarize, this is type of crystal structures that we can make from our simple approach. You can change cadmium, and this is a transition metal. You can go lanthanides and zinc and so on. And I'd like to thank people who are really impacted in my life, starting with my master PhD, with my master's, Dr. Rafat Abdelhamid, Bill Geiger at the University of Vermont for my PhD, and Professor Alan Bond in Monash University in Australia for my postdoc, and Professor Khalid Al-Farhan in King Saud University. And as Egyptian inspiration, this is some of the old, maybe Dr. Mustafa doesn't recall this, but that was in ACS meeting in 2007, and we have this kind of meeting. This is to show the beauty of Egypt, and you're most welcome. It's safe and nice. And I would like to thank you. And Cobalt Man, actually, it is my nickname, because always my success comes with the Cobalt first, and thank you for your attention.
Thank you, Dr. Amin. So the floor is open just for one question.
Yes.
Thank you for a beautiful talk. Have you guys measured the conductivity for the TCNQ MOFs with respect to different metals, and do you see changes in the conductivity?
Yes, that's a very important point in this work. Actually, we follow Kim Dunbar in Texas A&M in making these materials, and she looked at this magnetism as well as the conductivity of these materials. And definitely, even within the transition metals itself, we find some kind of differences. The only one that shows a phase change is, we don't know why, but only copper and zinc, which can exist in 2 different phases or polymorphs. The remaining transition metals only exist in 1 phase. So silver actually and copper, they having that kind of switching effect where they can go from insulating to conducting upon radiation with light or electricity. But the other remaining with the lanthanides, they have magnetic properties that are driving this kind of research. But definitely, yes. And TCNQ alone, it is insulating. It is insulating, yeah.
From the lady section, any question?
Yes.
Yes?
Yes, Assalamu alaikum.
Alaikum salam.
Thank you for amazing talk. Just I would like to ask you about when you use iron 2 as a metal, it is like difficult to stabilize the crystal, because sometimes when we try to grow crystal iron 2 and iron 3, there is like a mixture, or did you do this procedure in the gloves box, or I'm not sure.
Yep.
Thank you very
You
much.
mean about the air oxidation of iron, right?
Yes, please.
Yep. Well, this is an important point because from electrochemistry point of view, if you start with iron 2, we normally purge with nitrogen to avoid the presence
Yes.
of oxygen. This is number one. Number two, our potential that we apply, it is in a reduction mode. So that means we're not gonna oxidize the iron. We actually, if there is any trace of iron 3 in solution, that would be reduced and converted to iron 2. So we purely form actually iron 2 with the TCnQ minus. However, if you start in the oxidation side as you oxidize back,
Yep.
there is maybe a chance for iron 3 to be detected after it released from the crystal. So in the crystal itself, it is iron 2, and then as it goes into solution, it is iron 3, and now you are in a positive potential. That could lead to an oxidation of iron 2 to iron 3.
Okay.
Yeah,
Thank
but
you
it
very
doesn't really affect the chemistry or the formation of the
Crystal,
iron
yeah, yeah,
TCnQ
yes.
material.
Thank you very much.
Thank you,
for that.
Dr. Ayman. We will limit our morning session for just one other presentation, and then we will postpone the two presentations after lunch. So, Dr. Muhammad Ahmed is here? Okay, you are here. Okay, okay. Please go ahead. Okay, the other Dr. Iman Zahrani and Dr. Tahsin would be after lunch, inshallah.
Okay.
Iman and Tahsin. Dr. Iman is around?
دكتورة أيمن الزهراني موجودة؟
موجودة.
Okay, then Dr. Iman, inshallah, after lunch we will do your presentation, okay?
Thank you.
My name is Dr. Yasir Aziz.
Maybe after.
After lunch it was, so I want it could be taken as the first talk
We will see. Depends.
because actually I have to leave for a while.
Okay, let us see. Let us see. I will see. Please go on.
Okay, Professor. Thank you very much. Good afternoon, everybody. I am very proud to be here in the King Saud University, and thanks for the chairman and thanks for the committee to invited me to present my work here. Today, I will shift a little bit from the last session, from the last speaker, and I will speak about different subject. I will speak about the using of a new material or a new polymer instead of using the commercial polymer. As we know, all the polymers coming from petroleum resources like polyethylene, polypropylene, polystyrene, all of us, we are using this. But today now, all the world now is speaking about a new polymer, so, or a new source of the polymer. So they are using now natural polymer. It's coming from maybe from the vegetables or from animals or from microorganisms. So today I will just speak about some of my project in University of Guelph in Canada. The work there is novel epoxidized pine oil modified with polyhedral oligomeric siloxane nanocomposite. So I will just give a small introduction about thermoset resin, seed oil and oxidized seed oil, technical methodology, result, and discussion and conclusion and future work. So as I said before, we will speak about polymer. As we know, polymer is thermoplastic and thermoset. So I will just focus today about thermoset polymer. As we know, thermoset polymer is thermoset resin for use in composite material. As we know, what is the meaning of composite? Composite is consisting of two material, matrix and dispersed phase. The matrix is maybe an organic polymer, and the dispersed phase may be filler like organoclay or any filler you can add, or metals you can use. So the composite should have good mechanical properties, good adhesive properties, good toughness properties, and good resistance to environmental degradation. The most important sources of the thermoset is coming from petroleum resources, and the most famous one is the vinyl ester resin. It's consisting from diglycol ether of bisphenol A with reacting with acrylic acid or mesacrylic acid to form the vinyl ester resin. It's containing vinyl group and hydroxyl group in the structure, which improve the adhesion and wetting properties and excellent reactivity due to the presence of vinyl group. But the problem here that you have high viscosity of this vinyl ester, so most of the people, they add styrene or mesacrylate to overcome of this disadvantage. The other one is the epoxy resin. It's also from diglycidyl ether of bisphenol A, and it's containing the epoxy group in the end. It's synthesized from the reaction of bisphenol A with epichlorohydrin by polycondensation. The epoxy resins contain epoxy group in the backbone, as we said before, is used in automobile assembly, aircraft, aerospace, and wind turbine blades. So there are some disadvantages of this epoxy resin, like brittleness, low elongation at break, and low impact strength, and poor resistance to crack growth. And also, as we said, it's coming from petroleum resources. To overcome of these drawbacks, we need to use maybe addition of an organic filler or use of thermoplastic particles, addition of a second rubbery phase, or as we said, we can use natural polymer. So natural polymer are divided to 3 categories. From microbial, is like polyester, polysaccharide, polyphosphate. Vegetable, like cellulose, lignin. As we know, lignin is coming from the plant. Plant is containing cellulose, hemicellulose, and lignin. So, and starch, rubber, protein, polynucleotide. Animals is almost similar to vegetable. I just only focus here about the oil. I have some project before I work in lignin, to blending lignin with different commercial polymer or with biodegradable polymer like polylactic acid or polyhydroxybutyrate. So we just only today we will focus about oil. Vegetable oils are characterized one of the cheapest and most abundant biological feedstock available in large quantity. Its starting material offer numerous advantages such as low toxicity, inherent biodegradability. The double bond in the vegetable oils are used as a reactive site in coating. They can also be functionalized by oxidation, like this structure here. So all the double bond here can make epoxidized. Epoxidized show excellent potential as inexpensive and renewable material for industrial application. As we can see in this chart here, this is the oilseed world production. In 2014-2015 is around 300, more than 300 or 410 million ton per year is produced. And the most important one is the soybean oil, is around 100 million ton per year. The most important city or country produce this oil seed is soybean oil is United States and Brazil. Argentina is around 100 ton per year. So the disadvantage of this epoxidized resin is low mechanical performance, low heat deflection temperature, which is important for production of the new material compared to epoxy resin. The internal epoxy group hardly accept nucleophilic attack, resulting in poor reactivity. So they overcome of this problem by increasing the time of curing. Sometimes take more over than 6 hours, and is not good for application in industry. To overcome of this problem by blending with conventional petrochemical epoxidized, so they make mixing between the commercial product and the epoxidized soybean oil to have to overcome of this problem. The other, to addition of the filler. Some work before previous by Gupta et al. They blending diglycidyl ether of bisphenol A from 10 to 30% with epoxidized soybean oil, addition of the hardener. As we said, that epoxy resin is containing of epoxy and the hardener, as we said in the, you can see in the commercial product. So after that molding, as we can see here, the 10%, 20% of diglycidyl ether showing increasing in the tensile strength and tensile modulus, and decreasing in elongation and impact strength. So this means that addition of any epoxidized will decrease the impact and elongation. So our strategy of my work here is value-added use of epoxidized soybean oil and plus lower the amount of commercial epoxy resin and lower volatile organic compound to have more sustainable end product. There are now a new bio-based epoxy. It's composed of epoxidized pine oil, bisphenol A, and benzyl alcohol. It's around 29% of epoxidized pine oil. And the hardener, there is a lot of different ratio of amines. We try first to measure how much the time will take this bio-epoxy to be polymerized. So by using FTIR, we make the reaction at 80 degrees C, 100 degree, and 150. We found that it will be cured at room temperature for 24 hours, then at 100 degrees C for 1 hour, and 150 degrees C for another 1 hour. So the post-curing at 150 for 1 hour, disappearance of the epoxy ring. The DCC, the dynamic curing kinetics, were followed by at different heating rate, 2 degree, 5, 7, 10, 20, and we found that the reaction start at approximately 34 degrees C, and the peak at around 75 to 120, and the magnitude of the exotherm increasing by increasing the heating rate. We calculate the activation energy by using Sanger method and Flynn-Wall-Oza method by these two equations, and we found that the activation energy of this epoxidized by Sanger is around 55 kilojoule per mole, and by using Flynn-Wall is around 52, is almost the same. So after that, we try to calculate to know the mechanical properties of this bio-based epoxy. So from the tensile strengths and the flexure models, we compare between the commercial product and the Supersep, the commercial new bio-based. We found that the elongation here is a little bit smaller than the commercial product coming from petroleum resources, but the flexure modulus strength almost the same. So we try, and here also the isotope impact strength also lower than the commercial product. So here we try to find our toughening of this bio-epoxy by different product to enhance the elongation and the isotope impact strength. But the difference here between the two products that we have here just only 19% compared to 0% in the commercial of the epoxy resin. So we used different types of siloxane. We use polydimethyl siloxane terminated with amine, polydimethyl siloxane terminated with epoxy group, and glacityl polyhedral agglomeric siloxane. We use around 5% of each and see what happened in the reaction between this and the bio-epoxy. So we blending bio-epoxy resin with 5% of polydimethylamine or polydimethyl siloxane epoxy terminated with epoxy or post-glacidyl, then addition of the hardener, mixing at room temperature, then vacuum, casting at room temperature for 24 hours, then heating for 100 degrees C for 1 hour, then 150 degrees C for another one to have a film. Then we cut the film to measure the mechanical properties. We found that the polydimethylamine terminated with amine with bio-epoxy give, and the polydimethyl epoxy give an opaque film. However, was using post-glacidyl give a transparent film. So we calculate also the activation energy of this product. We found that the activation energy increasing comparing to the bio-epoxy, the neat bio-epoxy. The FTIR also showing disappearance of the peak of epoxy for all and the presence of SiOC of post-glacidyl at 1100 degree. So this means that we have a good interaction between the post and bio-epoxy. To measure the both lifetime of curing of this product, we measure the complex viscosity by using rheology. At room temperature with fixing strain at 1% and fixing angular frequency at 1 radius per second, we found that all the bio-epoxy blend are increasing in the viscosity, but the bio-epoxy with post-glacidyl is more increasing. This is due to the excess of glacidyl group which found in the post structure. The scanning electron microscope of this bioepoxy, we found that this is neat bioepoxy without any toughening agent. After addition of 5% polydimethylamine and polydimethyl glycidyl, we found some sphere, and the sphere has flat and board can be found, which suggests that we don't have any compatibility between the bioepoxy and the PDMS. However, by addition of 5% post-glycidyl give us a homogeneous phase. We tried to do the TM for this post-glycidyl. We found that we have the domain size of post-glycidyl is around 20 to 60 nanometer, and we found some agglomeration also from 60 to 100 nanometer. This is due to the steric hindrance of the post-glycidyl, which provide inhomogeneous distribution of post-glycidyl with the matrix. So we suggested the mechanism, what happening in the reaction between post-glycidyl and polydimethylsiloxane with the neat bioepoxy. So as we can see here, this is PDMS terminated with amine or epoxy, and this is bioepoxy, the neat bioepoxy, and the X is the hardener. So after curing, we found that bioepoxy there is no any linkage between each other, so it give us a phase separation. However, by using post-glycidyl, it's containing a lot of epoxy group in the terminated here, so give a network structure, which give as shown in the TM and the SCM. The mechanical properties of bioblend, as we said before, that we have two defects in epoxy resin, the elongation and the impact strengths. So the tensile strengths and the flexural strengths and flexural modulus almost the same. There is no change, slightly increasing here, and this is a good enhancement by just only 5%. But what's interesting here that elongation and break increasing by using 5% post-glycidyl, and also impact strength also increasing from around 32 to around 42. And each sample of this one we tested around 10 times to have with standard deviation. The heat deflection temperature also, which is important value here, increasing from 61 to around 70 degrees C. We making some thermal properties to see also the glass transition temperature here also are decreasing, indicating the good homogeneity between the bioepoxy resin and BOS glycidyl. Dynamic mechanical analysis for viscoelastic analysis, we found that all the bioepoxy resin are decreasing comparing to neat bioepoxy, and the glass transition temperature from the curve of tan delta almost give us the same value of the DSCC. Thermal analysis didn't show any change of degradation. This good indication that we have a long chain of aliphatic, but didn't affect in my material in the end. So we prepare a new hybrid system based on bioepoxy and 5% functionalized siloxane, and we found that 5% post-glycidyl had the best value and the best properties compared to the other filler, and can be a good candidate to enhancement of epoxy resin. So after we finished this work, we completed, because the aim of this work from the beginning to prepare a wind turbine blades, and instead to using the commercial the epoxy resin, to use a new material from renewable resources. So the new green renewable resources of this material will be applied in vacuum assisted resin transfer molding, and we will add a new filler to this one. We will use a soy stock and flax fiber to be increasing the amount of bio-based content in our product. Then we make a pilot scale commercially processing of soybean green composite for wind turbine blade. We will speak about this maybe in the next presentation, in the next seminar. Thank you. I would like first to acknowledge the Natural Science, NSERC, and Ontario Research Fund and my BDTC group. Thank you very much.
Thank you. The session now is open for talk question.
Thank you, Dr. Muhammad, for your presentation. I'm asking about the optimum ratio for blending of epoxide oil bean with synthetic one, and also what's the maximum, properties you got, and what's the best conditions for this blend to get, more properties.
Yeah, we try different ratio. We try from 1% to almost 30%, and we found that the 5% give us a good result for mechanical and morphology. This is the best one. But you know that we use now bioepoxy is containing 29%. So we don't like to add another organic material coming from commercial resources, from petroleum resource. So we don't like to increase. Maybe 10% also give us a good result. But 10 to 5 is almost the same result. There is no any change. Okay?
Thank you.
From the lady section? From the lady section? Any more question? If not, then let us thank you again.
No problem.
Now the session is closed, and have a good lunch. See you after lunch, inshallah.
يلا يا دكتور أيمن.
أبدأ خلاص؟
You can start, Dr. Ayman.
Yeah, okay.
Go ahead.
Yes, okay. Hello everybody. My name is Iman Al-Zahrani. I'm assistant professor of analytical chemistry. Today I'd like to talk about my work, which is about fabrication of the polymer-based microchip in order to use it for protein extraction. I'm going to divide my talk into 3 sections. First of all, I'd like to talk about background and objectives of my work. Then experimental part will be explained. After that, results and discussion will be discussed. Finally, conclusion and further work will be outlined. Okay, I'd like to tell you that my work is related to proteomics. So what is the meaning of proteomics? Proteomics can be defined as the study of the entire complement of proteins expressed by cell, tissue, or organism. Why is it difficult? The study of protein is very difficult because, proteins in biological samples are highly complex. Besides that, we have different range of proteins. So we have different types of proteins that vary in terms of molecular weight, isoelectric bond, and hydrophobicity. Besides that, the life of proteins is very short. Move on to the main steps of proteomic analysis. So the first step is extraction. We extract proteins from the biological sample. After that, we separate proteins from, the extracted proteins will be separated. Then the separated protein will be digested using enzyme. The next step is study of proteins using mass spectrometry. Finally, protein will be identified. My work just concentrated on the first step, which is about extraction. As you know, sample preparation consists over 80% of the total analysis time. Commonly, we can use solid phase extraction in order to remove interfering materials and to pre-concentrate proteins. Now, we'd like to know the main steps of solid phase extraction. The first step is condition. We need to condition the sorbent. After that, we apply the sample in order to bind the protein or interested analyte to the sorbent. Then we need to wash the sorbent in order to remove interfering materials without affecting the interested analyte. Finally, elution step. We need to elute the interested analyte in order to study. My work just concentrate on fabrication of sorbent. Now I'd like to talk about the types of sorbent. We have different types of sorbent. We have particles and we have monolith. Let's start talking about particles. The main advantage of particles is the high surface area. So the important thing if you want to use a sorbent is the sorbent should has a high surface area. But we have many disadvantages of particles. One of them, it isn't easy to fabricate it. Besides that, it isn't easy to fill the column with with particles. The main problem for me, I think we need to use a frets because we need to hold the particles inside the microchip or the microchannel, so we need the frets. Therefore, I decide not to use particles. Monolith. Monolith, it is a Greek word. Mono, which means one. Lithos, which means stone. That's mean one stone. As you can see here, photograph of the porous monolith at the entrance of the Summer Palace Park in China. If you see that porous monolith, it is one single piece, has different size of pores, and it should be has high surface area. We have two types of monolith. The first one is silica-based monolith, and the second one is polymer-based monolith. I worked in both area. However, today I just like to talk about polymer-based monolith. Now you have a clear idea that I'm interested on fabrication of polymer-based monolith in order to use it as a sorbent, but in fact I'd like to fabricate it inside a microfluidic device. The reason of using microfluidic device, because it is a portable, so it will be very easy to carry it, especially for ladies. Besides that, we can reduce the volume of the sample. Sometimes it's not available in enough amount. It's very important for us to decrease the volume of reagents, because sometimes, as you know, it's very expensive or it isn't available. We reduce the volume of the waste, and the important thing for us reduce the analysis time. So now we have a clear idea what is the main objectives of my work. Firstly, fabrication of the polymer-based monolith. Then using the fabricated materials for pre-concentration of proteins. Finally, if we manage to do that, we can move and fabricate the material inside a microchip. Okay, let's move to the main steps of fabrication of the polymer-based microchip. The first step is filling the column with polymerization mixture. The polymerization mixture consists of monomer, cross-linker. The monomer is butyl methacrylate and the cross-linker ethylene dimethacrylate. As you know, we need initiator and we need to use a binary borogenic solvent. In this study, we use methanol and organic solvent. The next step, we need to place the column under the UV lamp at 365 nanometer, and then the next step or the final step, we just need to wash the column in order to remove the interfering materials. You can see here we fabricated different monolith. Just here we use different organic solvent. The main solvent is methanol and we use different organic solvent. After washing that, all of these fabricated material, you can see the best porogenic solvent is methanol and propanol, and the reason for that, the diameter of the monolith wasn't changed, so we decided to use that organic solvent. Okay, we decided to fabricate it inside the column. So this is borosilicate column and we fabricated the polymer-based monolith inside it. The length of the polymer, the monolithic materials, is 6 millimeter. It's very important to study the morphology, the structural morphology of the material. So this is a scanning electron microscopy of the polymer-based monolith that fabricated, and you can see here it's very important to get a homogeneous material. Okay, we are happy about fabrication. We need now to check the performance of the monolithic materials in order to use it as a sorbent for extraction of proteins. I use different proteins, cytochrome C, myoglobin and hemoglobin and myoglobin. The reason for choosing that proteins because they are colored protein. So if there is any change in the sorbent, it will be easily to know if there is a difference or not in the monolithic material. So this is the first step, and you can see here applying sample. I'm sure you remember the color of the monolith. It was white. Now the color changed. Depends the color changed to the color of proteins. For example, cytochrome C red, hemoglobin and myoglobin brown. After applying sample, washing, and washing with ammonium acetate, and you can see here the collected solution. The collected solution of after washing step, it was transparent. That's mean washing solution solution didn't change or affect the binded proteins. Finally, it is the elution step, and we eluted the pre-concentrated protein, and then it will be ready to study it. So from the color, the change in the color of the monolithic materials, that give a good indication that it will be a good sorbent for use it for proteins. So the next step is we need to fabricate it inside a microchip. And as I mentioned before, because the microfluidic devices have many advantages compared to the conventional method. And this is the design schematic diagram and photograph of the glass microchip, and you can see here filled with a blue food dye for visualization. And you can see here A is the extraction chamber, so we fabricate the monolithic material inside that extraction chamber. Here a photograph, we just compare. If you see the color, the extraction chamber contain the monolithic bit, change from white to red, because here we use cytochrome C. This is give us a good indication that the monolithic material, the organic monolithic material, is a good sorbent for proteins. Here I'd like to show you the extraction recovery of the standard proteins purified with the polymer-based monolith, and that use fabricated inside the glass microchip. And all of these proteins vary in molecular weight, isoelectric point, and hydrophobicity. Finally, I'd like to tell you that in conclusion, a novel microfluidic device has been fabricated successfully. We are quite happy about the performance of the glass microchips in terms of pre-concentration of proteins. The microchip, it was stable over time. Further work, I think it will be a good idea if we use a real sample. Besides that, I think it is a good idea if we integrate the existing microchip, for example, reduction and alkylation microchip with that microchip. Finally, thank you very much for your attention. If you have any question, I'll try to do my best to answer all of your questions. Thank you.
Thank you, Dr. Fatma. The floor is now open for only one question from the lady section. Because we are running, Dr. Iman, sorry, Dr. Iman. We are running out of time.
Yeah.
Only one question.
Yeah, do you have any question, please? Yeah. They don't have any question, Doctor.
Then thank you very much.
Okay, thanks.
The next speaker is Dr. Tahsin Kamal. Is he around? Okay, please.
So first I will introduce what are actuators, their types, and liquid crystal polymer based actuators, and what are the limitations of the currently used actuators. After that I will proceed to my research work. So what is an actuator? Actuator is a kind of sensor which responds to a motion, which responds to certain stimuli as a motion. So in a typical fabrication of a bilayer actuator, an active material is adhered on a passive material, and upon application of stimuli, volume change of the active material happen. As a result, this whole system tries to curve and it bends. So if it is made up of polymer, if this is polymeric material, active material is of polymeric in nature, then on molecular level, these polymer chains extends upon application of the stimuli. So non-liquid crystal polymer based bilayer actuators, as the name expresses, it uses two layers of polymers like the polyethylene, low density polyethylene, and NiPAM monomers along with SWNT were polymerized on some specific spots on this polymer, and upon heating the system for this polymer film, it folds up. We can see from the real time pictures of their experiment that a single 2D, two-dimensional sheet, it converted into a 3D cube like structure. So single layer non-liquid crystal polymer based actuator. As the name expresses, the film is composed of a single material. In this work, the author presented that the film was of polyethylene nanofibers, and they flash welded one side of the polymer film. So we can see the difference in these two images, and same image along the film thickness revealed that it had one strongly cross-linked surface while the other free nanoporous structure. Upon exposing this film to acid, it curled, and again upon exposing the film to a strong base, it again adopted the original shape. So what are liquid crystal polymers? Liquid crystal polymers bear some special moieties like this one, cyanobiphenyl moiety, and connected to the polymer chains. So in monodomain sample, all the mesogens are oriented along the nematic director. They are in same direction. Upon phase transition, these mesogens lost their orientation, and stress from the polymer chains is reduced, which causes the whole film to shrink along the nematic director while it expands perpendicular to the nematic director. We can see the real images of their experiment that upon heating, these shrinked along the nematic director and expanded perpendicular to the nematic director. So how these films were produced? For these, two types of LC cells are used. One are called planar LC cell, and second type are twisted nematic LC cell. It produces polymer film with the which can adopt a shape like this one, and for a twisted nematic cell, the film produced show actuation into a curling motion. Sometimes functional moieties are introduced in the liquid crystal polymer films, and they can be used for different purposes. For example, upon exposing to different level of humidity, it shows humidity dependent curvature in the film. So what were the limitations in previous works? Like they were taking quite longer time. Polymerization takes quite longer time, and mostly bilayer actuators were demonstrated. Bilayers, after few cycles of actuation, bilayers delaminates. They separates from each other, and most of the time temperature and light responsive liquid crystal polymer actuators were produced, and there is no report on the 3D actuation from a liquid crystal polymer single layer actuator. that I used monomers get dissolved into a solvent, and after polymerization it phase separated out from the solvent. Also I explored different effects of the compositions of the monomer and monomer mixture and thickness of the film on the actuation speed. So the material I used in abundant, I use this monomer. It is a diacrylate monomer. It is at room temperature, it is in liquid state, but it is in liquid crystalline state. And I use photoinitiator so that photopolymerization could be performed. I screened out what compositions will be necessary for the photopolymerization, and there were 3 compositions which could be successfully photopolymerized. Here is a procedure for the film preparation. So I used planar LC cell, then I injected the mixture of monomer with solvent. Solvent was 5CB. Then I photopolymerized it for 2 minutes. After opening of the cell, I found that it formed a film on the 1 glass slide. And after that, I explored the characteristics of this film. So I determined the swellability of this polymer film. I used different solvents, almost 13 solvents, and swelled small polymer piece in these solvents. I found that acetone and chloroform were the best solvents to swell this polymer a lot. And water was a non-solvent for this polymer. In further experiments, I used only acetone and water because acetone and water are miscible with each other while chloroform is not miscible with water. I revealed the morphology by SEM. We can see that the UV exposed side of the polymer film, it has no morphology, while the other side of the polymer film is quite porous. It means that phase separation happened during the polymerization of this film. Also, I performed the wide angle X-ray pattern. I recorded wide angle X-ray pattern from this polymer film, which showed that the molecules, mesogens were aligned along the rubbing direction. So in dry state, the polymer film was in curled state. We can see this one. While putting this into acetone, this polymer film opened, and again putting this film into water, the film curled again. I characterized this motion by radius of curvature, as we can see schematically. Oh, it's okay. And this motion was quite repeatable up to many times. So it's quite interesting because it's a single polymer film, but by changing solvent quality for this film, it shows motion. Okay, next I used different acetone and water mixed solvents, and I varied the acetone content in water. We can see that the composition dependent curvature was obtained in these experiments. I also made polymer film, actuator film with different thicknesses, and because actuation time is also important for actuators. So here is a 250 micrometer thick film, which showed quite longer time for full opening of this actuation motion. while the next polymer film, which had a thickness of 168 micrometer, it showed a slight quicker response to the solvent. Similarly, the most thinner film, it had high response time. It has this is 168 micrometer thick film. And this is the last one, which showed quite fast response to the solvent. Conclusion from my works was that I prepared a single layer actuator that was liquid crystalline polymer based. And the actuation of this actuator was due to morphologically asymmetric structure along the film thickness. Actuator also showed solvent mixture dependent curvature, and actuation speed was dependent on the film thickness. Thank you very much. Any question?
Thank you very much, Dr. Tahsin. Now the floor is open just for one question. If not, then we have to welcome you again. Thank you, Dr. Tahsin. Afternoon session. Sorry for the delay, but it was out of our hands. We started very late.
Good afternoon, everybody. Thank you all for being here. And I would really more than happy to presenting this session. So first we'll start with Professor Bisquart. So I would like to give a very short biography about him. Professor Bisquart is a professor of applied physics at University Guillaume I.D. Castillo from Spain. He is the director of the Institute of Advanced Materials at the University sorry for the interpretation. He conducted experimental and theoretical research on nanoscale devices for production and storage of clean energies. His main topics of interest are materials and processes in perovskite solar cells, nanostructured solar cells, solar fuel production, and lithium battery. He has developed the application of measurement techniques and physical modeling of nanostructured energy devices that relate the device operation with elementary steps that take place at the nanoscale dimension. Charge transfer, carrier transport, chemical reaction, etc., especially in the field of impedance spectroscopy, as well as general device models. He authored 300 peer-reviewed papers and reference book, Nanostructured Energy Devices, his H-Index 65, and is currently a senior editor of the Journal of Physical Chemistry and member of the editorial board of Energy and Environmental Science and Chem Electrochem. He has been distinguished in the 2014 list of ISI highly cited researchers. So let's welcome Professor Bisquart and start the talk with him.
So it's a pleasure to give a talk here. And what I will do today is first some revision of nanostructure solar cells, and then speak about the properties of the new perovskite solar cells. So to begin, we start with the dye-sensitized solar cell, which has this fundamental structure. So a solar cell normally is an absorber material, and then you need, from this absorber, you will get electrons and holes by photoexcitation, and then you need to extract selectively electrons on one side and hole into the other. So in the dye solar cell, here is the electron contact is normally titanium dioxide, which is a wide bandgap semiconductor, so it cannot accept holes. And then what we get here is an increase of this Fermi level, and then the hole that is generated here by light, we can transfer to some hole transfer material. That could be liquid electrolyte or could be some polymer, for example, like spirometad. Okay, so this is one realization. So you see, this is the crystalline titanium dioxide. So this is the bipolymer structure, which is truncated here in phase 100, and this is totally crystalline. So then you anchor a dye. Most famous dyes have been developed by Nasseruddin and Zakheruddin that are here these days. So then you do a good match for rapid electron transfer, and so you will do rapid electron injection to the semiconductor. So this now has to transfer, it's oxidized, has to transfer a hole. So this is the other reaction. So then you get electrons at this side, holes, and the other, they are well separated, but will meet again by what we call recombination. So this is the main problem of all solar cells, is to control recombination, because then you lose your carriers inside and you have nothing. Okay, so you want the carriers to go outside to do electrical work for you. So when there are very interesting properties. So the dye-sensitized solar cell has not been so viable device in terms of technology, but it opened many ideas about the behavior of nanostructures and gave rise to many things. So when you use this sensitizer, this has a very small extinction coefficient, so you need bigger area. So the way to have bigger areas to do a porous structure that is represented here, so you can collect electrons all the way. So then electrons collected far away from the contact will have to travel to the contact. So then they will go around and meet here with an oxidized ion. So this is the closing of the circuit. So we have very interesting phenomena of the transport of electrons in disordered materials, and this has been widely studied by us and by many other people. So one method we developed that's a long time ago, around 2000, was to study this nanostructure. This is the picture of one of the first one, made in 1995 in Berlin, in Germany. And then we wanted to study how the transport of electrons is going here. So we applied this technique of impedance spectroscopy that has been a lot used in electrochemistry. But here it takes another meaning, because when you study impedance spectroscopy in solar cells, it's not only charge transfer at interfaces, which is the classical application in electrochemistry. You have also electrical elements are related to charge transport. Okay, so this is combined, and the spectra have a lot of information about that. Okay, when you understand them, sometimes you don't understand them, and the information is there, but you cannot see it. But this problem we could understand, and the way to understand it is to formulate this type of transmission line circuit, in which we have resistance for electron transport, and then here we have the charge transfer and charge accumulation element. So all this give rise to this spectra. So this we understand very well, and it has been applied by now, hundreds of people, and people learn it. So you can have this particular spectra. This is the first one that was reported, so 45 line. This is electron diffusion around here, okay? And then here we have capacitance and charge transfer resistance, which are here. And then sometimes you have more things, 1, 2, 3 arcs. Okay, so this is also nice information because, of course, in the solar cells you have not only the active layer, we have electrons and holes moving. In solar cells, you always have contacts, and contacts are a very critical part of the device because this is where you extract your carriers, as I said before, so that you have additional elements. These give other arcs. So this is a good way to characterize, for example, a dye-sensitized solar cell. We'll find more information because this structure here, this is like amorphous semiconductor. It's not like a crystalline semiconductor. There is strong disorder. Disorder means that you just don't have the band gap, but you have a strong density of states in the band gap. And then what happens is that when you modulate the voltage in the solar cell, which is like the Fermi level here, you change the occupation of these states in the band gap. And in the end, with voltage, you can really scan the density of states. So this is the typical density of states of anatase titanium dioxide used in dye-sensitized solar cell and other applications. It's an exponential distribution, so that when you move the voltage in your contact, what you're moving is the position of the Fermi level, so you are feeling the density of states. So really by a scan of voltage, you can see the density of states, and this you can do by cyclic voltammetry, or you can do it by impedance spectroscopy, like I show here. Okay, so you see this is the voltage, and this is exponential scale, so this is really totally exponential plot of the density of states of electrons in titanium. This is the conduction band. That's very important because that is where the dye injects. We cannot get up there. But we can see something very important, which is a shift with respect to energy levels on the electrolyte. For example, if you put a dipole oriented this way, all the levels go down. So at the same voltage, you get more charge density. So at the same voltage, you get more charge density. So you see this shift. This is something essential in order to see the energetics of your titanium dioxide. And this is very important information you can get from this type of analysis. So this is called the chemical capacitance because this capacitance arises just from the distribution of electrons in the density of states. And this is something you can measure for any disorder materials. This is related immediately to the density of states, as shown here. So this is a plot of the same concepts. Now you can see here the density of states. We put the Fermi level, and then we get this important formula, which is that the chemical capacitance is really like the density of states. So based on the recognition that we can identify the chemical capacitance of this density of state with respect to reference energy level, which is the redox potential in electrolyte, we can make this total map. This is a total map of energetics. This is the drawing I showed at the beginning, which was approximate. But now here is totally quantitative, and you see something here commented already by Anders Hagfeldt and other people. This is the iodide redox couple, okay, and this is ground state of dye. You see, this is a very big difference, which is main problem of the dye-sensitized solar cell. You lose here 0.7 to 1 volt. You lose it for dye regeneration. So then they were developed the redox carriers with cobalt, like here, and then it's much higher voltage. So with respect to this reference, we can plot now the density of states, and we can know also the energy level of the dyes. So we can do a very good characterization in order to optimize the dye solar cells. So the dye solar cell historically was optimized using two devices. One is to lower the redox level of the whole carrier. The other one was to bring up the conduction band. Okay, this bringing up, because when you bring this up, then you get higher photovoltage because the Fermi level goes higher. So here's how they reached a very big voltage. And of course, you have a limit to bring it up. With this dye N719, you cannot bring it higher because then the dye will not inject. Okay, so you have to tune it to the right place to increase voltage. And this is the study that we can use to optimize the dye solar cell. Okay. So then I will do, we did this type of analysis with organic solar cells. This has been discussed before, especially by Antonio, so that I would just go to the point of applying this technique. And now in the organic solar cell, it's a little bit different. Let me see if I have, no, I don't have this scheme. It's a little bit different because in the organic solar cell, we don't have 3 materials, we have 2. So the absorber is the same as the whole transport material. So what you do is you inject an electron to the electron transport material, which is fullerene. Okay, so that from the first excitation, you will go to the electron transport material and leave a hole in the PCST, for example. So that what we have in these materials is strong doping, like here, like we have the whole Fermi level, and then you will bring up the Fermi level of electrons in the fullerene. So then you can do the same as I said before. As you bring up the Fermi level of electrons, you scan the density of states of electrons in the fullerene. And you can define, of course, the chemical capacitance with the same meaning as before. And so here is one measurement. Here is another one. So this is the chemical capacitance in the fullerene, which is like exponential, although many analyses of disorder in polymers say it's a Gaussian, could be a Gaussian, but very seldom we see a Gaussian. We cannot go up there. Okay, so and this Gaussian would be, this is not right. This Gaussian would be in the middle of the band gap because this is just 1.2. So the band gap, the Lumor conduction band would be like up here. Okay. So now this technique has been applied extensively for identifying the energetics of Burke junction mixtures. So here we have a lot of them. Of course, this PCD-TBT and the fullerene with 70, this is giving the higher voltage, okay? Because this, again, has the highest difference of the energetics of electrons with respect to the electronic polymer, okay? So that this is the most efficient solar cell, and we can see that in part, this is because it has best energetics, okay? But it's not only energetics. You can see here the energetics, this PCBM with the density of state. Then you have PCST with the density of states. We can see here the chemical capacitance, and when we compare different types of fullerenes, for example, then we can see becoming higher for as I said before, no, the higher is ICBE here, is higher, so it will give the higher voltage. And another thing which is very important is how then charged electron carriers are transferred from the PCBM to the PCST, because this is now the recombination. Okay, so you always have to measure 2 things. One is the relative density of states of the 2 materials, because this tells you when you put a number of carriers what will be the photovoltage. But how many carriers do you have? The number of carriers you have depend on recombination, because the carriers are out of equilibrium and they turn back. So you have to measure 2 things. One is the rate of recombination, the other is the density of states. So this, as I said before, we could do very successfully in the dye solar cell, where the map is total, and you can measure rate of recombination, and did successfully here also in many types of organic solar cells. So now I come to the perovskite. The other things took about 10 to 15 years. In the perovskites, we have been like 2 years working now, and the progress is very slow, I must say. So we have a lot of things to understand. So today I will give some opinion. So ideally we should do the same thing as here. So ideally, in all solar cells, we have this structure, and the perovskite must have the same structure. So you have a lot of stories of contacts, etc., but in the end, you are accumulating carriers, so that you must have somewhere a big chemical capacitance. Okay, And then from this chemical capacitance, you have a parallel resistance, which is loss of electrons, and that will be recombination resistance. So that will be the critical thing for the perovskite solar cell, but we didn't find it. We don't know where it is. So it's a big mess, okay? So the story I tell you today is not very nice, but this is the story I have at this moment. So to begin with, this is the structure of the perovskite. All this has been very well explained by Dr. Nasseruddin this morning. We can see ionic, we can see the separation of conduction of valence bands so that electron transfer is like ionic character, so the electron is transferred from one place to the other. And another important thing of this structure is polarization. Polarization is something very important. And when we used to study the diacetyles for a solar cell, this was a critical study, because when you create electrons and holes, you don't want to make space charge. You cannot make space charge. Nasser mentioned this morning. If you put electrons here, you need holes or something to accompany. Okay, so and this is a critical factor of any device. So in the diacetyl solar cell, as I said before, we were injecting a lot of electrons in the TiO2. The electron charge was increasing enormously, up to, you can put 10, 20 electrons per particle. But we had something very nice, which is electrolyte. So electrolyte has supporting electrolyte. So it has a lot of ions that can move around, like lithium. Well, lithium not very good, but you can put other salts with positive charge. So if I put a lot of electronic charge in the TiO2, then simply I have a bulk reservoir, then positive charge comes in, compensates, and makes shielding. Shielding means that there will be no space charge, so that you don't have limitations to distribute space electrons. Okay. So here, what I'm going to tell today is that we have this is not an electrolyte, of course, but somehow it is, because some of these ions, especially methylammonium, and some interstitial iodides, this is mobile. So by definition, an electrolyte is something that can move ions, okay? But this will not be really an electrolyte, because in electrolyte, you don't want to carry electrons. So you want to make a battery, you want to transfer ions, but you don't want the electrons to go through, because this will short, okay? So this is called a mixed conductor, because it will move, you can move electrolyte, ions like an electrolyte, and it can move also electrons and holes like a semiconductor. So this is the worst thing you can find for characterization. Why? Because you apply a voltage, and you have a lot of possibilities then. You can be moving electrons, or you can be moving ions, and you don't know what you're moving. And it's very difficult to distinguish what you're moving. It's not easy at all, and nobody has done it, so we don't know what is moving, because nobody has measured partial conductivities. Okay, to measure partial conductivities, you need special type of contacts. Contacts, for example, that would be selective to iodide and conduct iodide, but not electrons. Okay, but when you put contacts made by iodide, these will react with the perovskite, and not good. So it's a big problem, but I announce you that this structure has peculiar characteristics. So one is polarity. This is polar. This is polar. So this can rotate. Whenever something is polar, if you put a charge, the polarization will move around and remove the charge by a factor corresponding to epsilon, the electric constant. Okay. So one thing that this is polar, and the whole structure is polar because perovskites. In perovskites, you have polarity for the cage. You can move one ion a little bit with respect to the other ones, and this is another dipole. In fact, the highest dielectric constant materials are perovskites. As barium titanite and these materials, you have a dielectric constant close to the phase transition that can go to 1,000 or more. Okay, and this is because a little click you make a click of one ion, and this small displacement makes a very big epsilon. Okay, and you can also have cage rotation. So these are things in the structure. So it's a organic, inorganic, and very soft structure. So this is something we need to learn to control. Okay, so here, for example, another possibility of distortion. So there will be, when these things become favored at a certain temperature, then this will change structure. So you have some phase transition. At room temperature, you have one from cubic to tetrahedral, and then you don't have any more symmetry. And at 150 Kelvin, more or less, you have another phase transition still. So this is a structure that can be transformed in many ways. And the main point, I am telling you all this talk because it happens that when you apply light or apply voltage, you induce very strong changes, because all these things can happen and do happen. Okay, so this is the challenge today, is that, okay, I have very nice solar cell, but I don't know how it works. It's not easy because the structure has this complication. This is something we really need to master. Okay, so this is a little bit history. So this was like a spring off of the dicey solar cell in the beginning. This was the work of Kojima and Tomi Asaka. So they could make a sensitized cell, leaving very little time. So then came scientific report. This is Nangyu Park, by putting the whole conductor. This is also something that was invented in dicey solar cell. So a lot of things happening here came from dicey solar cell. But then new properties appeared, and this is, for example, the method of Lausanne. This is built over TiO2. That will be a very good framework, and it will take it will take the perovskite inside and in additional layers, so that this will help conduct electrons like in a dicey solar cell. But this is not necessary. This is not necessary because you can make a thin film, so that the perovskite is a bipolar electron and hole conductor. So you don't need it. But up to today, this structure is more robust and more efficient than the planar. But we are very much interested with the planar because nanostructure is also introducing complications. So this is something, but this contact works much better than this one. This is a very big reality at this moment. So we are doing, again, the impedance spectroscopy, and I explained before, for example, that we have typically 3 arcs in a solar cell. The arc in the middle is the important one, because this is the accumulation of electrons, and then you have one arcs at higher and very low frequency. This is normally something of contacts, depending on electrochemical contacts. But at this moment, this interpretation is not. We wrote some papers, but they have to take in with a lot of caution. Our papers and the rest of the people's papers also, because some things have not been confirmed, and there can be, okay, it's not that papers are wrong, it's that in other cases this may not be the right interpretation. There are, because I said, different possibilities are appearing. So what is different in the perovskite solar cell with respect to the others, which were difficult nanostructure solar cell, but in the end we could achieve a very consistent interpretation? So here there are very new and distinct phenomena. So the first one is that when we measure, like the capacitance, I said before, is a very critical, important thing for us because we need to recognize the chemical capacitance. But here, the capacitance goes extremely large, very large, and it is light dependent. So it is impossible that this capacitance is a chemical capacitance, because it's huge capacitance. So this is something that we had not seen before in any solar cell. It's something radically new. The second thing is this giant switchable. Okay, switchable is very important. You see, this is my solar cell. Now it has this IV curve. But if I polarize it for some time, I can invert the IV curve. And now this is the same device, but the P contact has become N contact and vice versa. So, so you can change the nature, you can invert the nature of the contacts. And this is hysteresis, which is something also, okay, this is not so new because dicey solar cells do have hysteresis, a lot of capacitive current, but here hysteresis means that really sometimes it's totally discontrolled. The cell characteristic changes depending on what happened before to the cell. Okay, so we will go into these things, which is the new things we need to understand, because it's we need to know the cause for these things in order to understand the solar cell, the perovskite solar cell. So this is one first characteristic. As I said before, this is like the capacitance as a function of frequency. So this is measurement in dark, and this is measurement in light. So in dark, we have an effective dielectric constant of 1000. You can say, okay, it's a perovskite. Maybe the epsilon is very large. But then you put light, and it goes 1000 factor bigger. So this we need to explain. At the same time, conductivity will increase. Well, this is natural, okay, because you are putting carriers with light. So we wish to increase the conductivity. This is not really conductivity. At low frequency, this is not a symmetric sample. So this is a plot of conductivity, but in a solar cell, the DC current is not conductivity, it's recombination, because the only thing you can have at low when you come to DC, when you pass steady state current, it's a recombination current always, because it's a diode, okay? But anyway, it's affected by conductivity, and it increases a lot. So I will go first to the thing of hysteresis, because we do have some starting idea. So now I want to remember some basic things of, like electrochemistry, you do scans of voltage. You increase a certain speed and then come back. This is voltammetry, and a lot of people know. So we measure some current potential curve, and this is also how we measure current voltage characteristic in a solar cell that gives us the power conversion efficiency. So what happens when we have a capacitance? It's not a diode, not a resistance, just a capacitance. If you have a capacitance, then the relation, the behavior of the current on the circuit voltammetry is as simple as that. So the current is the scan rate, the velocity of the voltage, times the capacitance. Okay, so because this is capacitive current. Capacitive current means that you have a capacitor and you can charge it with time. So as long as you change the voltage with time, you are charging the capacitor. If you stop, the current goes away, and this is capacitive current. Okay, so that's it. So what will happen if you have a constant capacitor is very simple. Under cyclic voltammetry, it will be a square plot, because when you go, S is positive, and when you come back, S is negative. So the capacitive current responds to your direction of potential. Potential increase, positive current. Potential decrease, negative current. So it's symmetric. And this is what real capacitor does. Not totally square, because you have edge effects due to resistance, but it's basically square, and this is totally well known. This is how you see a capacitor. So in a solar cell, it's a little bit different, because you don't have only the capacitance. You have JV curve. JV curve is not transient, it's a steady state curve. In fact, this is the important one. Okay? So for a solar cell, the transient effect is not significant. It's significant what you can, the current you can keep for 5 hours constant. So these points are constant. But so this is JV curve in a solar cell. But now you add capacitive current. So it's positive, negative added, so it opens up here. So that would be one kind of hysteresis due to capacitive current. And now this is demonstrated by my friend and colleague Germán García Belmonte, so that you can see here, this is a perovskite solar cell, but this is in the dark. Okay, so now it's very important when we talk in the dark without added electrons, and we talk in light today, because in light we don't know what happens. But in dark we do know, thanks to this work, that if you do scans at different velocity, then you find this square opening of the JV curve, and you can show that you can subtract, for example, the steady state curve, and then you have the totally square capacitance, independent of voltage in this case. And you can see that the capacitance is the capacitive current, this one, is proportional to scan rate. So this is the showing that you have capacitive current, and you can calculate the capacitance. So for the dark, we see that we have a big capaciting current. Why? Because the perovskite solar cell has a big capacitance. So it shows you opening, all right? So now this work was done by Bo Chen and also Kai Su, and they contact us for interpretation. So it's a very nice work because we know the capacitive current, but the perovskite has another current that is not capacitive. But they succeed to make cells that are very, very, very capacitive. So the hysteresis is totally capacitive. And this is very beautiful because when a capacitive has a transient decay, so the hysteresis here is very easy to understand. You have a decay, so if your voltage step is done very slowly, in each case the decay goes to the IV curve. And it doesn't care if you go forward or backward, you do the same. But if the voltage step is faster, the decay cannot go to the bottom line. Okay, so that's what happened here. The decay cannot go to the bottom line, so then you never reach the JV curve. Or here you can see that the opening around the steady state curve. So this is pure capacitive current giving hysteresis in this case. But there are other cases where this is not what happens, because capacitive currents is symmetric, so you cannot move the photocurrent. And in other cases, we are seeing that the photocurrent is coming from here to here, you see. So this cannot be capacitive, this is something else. And this is a big effect. For example, this is the paper by Borg-Ventress and Gratzel and others, and here. So yeah, this is your paper. So that you see here that you're moving the current by scan velocity from here to here. So this cannot be capacitive current because it's not an added current. This is that you are changing the operation of the steady state current somehow. So there are two different causes of the current. One is capacitive, another non-capacitive. So now we come to the issue of ion immigration. And the idea is that ions can move. They will go to the interface because they cannot go further than that, like electrons. So there's a very big difference between electron conductor and ion conductor. Electrons can enter the metal. Ions cannot enter the metal. So ions cannot give DC current. They do give current at some frequency, but when you go at low frequency, they can give only capacitance because they accumulate on the interface and cannot go further. Okay. So this is a study made by the team of Filippo De Angelis, and I was giving some idea also about hopping of the ion migration you see going from one interstitial to the other, and calculation of activation energy. And this is the iodide vacancy, we cannot see very well, which has very small activation energy, like 0.1 electron volt, so this is very likely. So this is the idea that when I create defects, then this is the semiconductor band, we will have different types of band bending and modify the nature of the contacts, okay? And this paper was published before the paper you showed this morning of Ahrens and these people. But anyway, the idea is very similar. And then we come to some observations that have been reported. First one, I think, was Eva Unger and McGee and the team, and they showed very drastic changes in the current voltage curve by polarization. So this was reverse polarization, and sorry, this was being degraded, and after further polarization, it was recovering like that. Okay, and this is the other way around. With negative polarization, you were degrading the operation of the solar cell, but it's reversible. From here you can go to here, and this was one of the first indications that you were doing some change affecting the operation of the solar cell, not just some trivial capacitive current. Okay, so more data has come about this. So, for example, this is the modification showing that the modification of the contact TiO2, including some fullerene, removes a big hysteresis in the planar cell. The planar TiO2 solar cell has a very big hysteresis by some reason, maybe related to my interpretation. But when you put some carbon material in the electroconductor, then you remove almost totally this hysteresis. And here is one very nice result by Ana Maria Petrosa and other people in the team that shows the electron transfer in TiO2. So it is lower than in this other material. You see, this is faster. But when you polarize the TiO2 close to BC, I mean in forward bias, then it becomes fast, like the other one. So that the good property of the fullerene, you can induce it in TiO2 only by polarization. This is very drastic changes shown by the work of Hagfeld and all the people in TPFL already discussed this morning by Dr. Nasser also, showing very big hysteresis when the TiO2 is made by atomic layer deposition. Here is the hysteresis, in addition to the bad injection of this atomic layer deposition TiO2, which is really bad with respect to the spray pyrolysis. And this is VOC decay. This is a classical technique that was pioneered by Arizaban and myself many years ago, and it was showing recombination in the disolar cell, but here it is not showing recombination. It's showing some other thing because there's a extremely slow decay here. You see it goes over to 10 seconds to remove the voltage. But this cannot be electrons. I mean, not even electrons in traps, I think. But anyway, here it shows that when you modify the contact, you affect a lot this decay. So again, I think it's an indication of the same thing. And here is again the question of the inversion of the photovoltage of the voltage of the JV curve I showed before. So this is done by Jinson Huang and his co-workers. So that would be migration of ions can change P into N, so that we have this structure of barriers induced by the coming ions. So for example, the iodide will accumulate here, the iodide vacancies here. So this will be like N, this will be like P, and then by applying another voltage, you can reverse this situation and make the other way around. This is not very stable, so because this ionic motion, you cannot control it. When you remove the voltage, it will slowly go away. So I think this can stay only for some minutes, less than an hour probably. But anyway, this is the picture in total, so that my first conclusion is that these control changes in the perovskite solar cell have two origins. One is that you have transients because of capacitive effect. Another one is that you have temporary modifications, slower, so the capacitance is scaled a little bit like 0.1 seconds or so. But then you have still slower phenomena, which is moving the ions and modifying the contacts, like in one case this one, in the other case the other. So now the question is, can we see that really with capacitance? Is the capacitance we measure related to that? So here comes some very classical thing, which is called electrode polarization. So this is a pure ionic conductor. This is glass with ions, no electronic conductivity. So this is the classical picture. Look at the conductivity as a function of frequency, for example. So this is high frequency phenomena, but we have DC constant conductivity. But when we go to very low frequency, this has to disappear, as I said before, because this is ionic conduction, and you cannot have DC ionic conduction. It's impossible, okay? Goes away. When the conductivity goes away at low frequency, the polarization goes up. And this is because you are building up ionic charge close to the electrode, not very different from electrochemical capacitance. You remember the double layer capacitance and Gui-Chapman, all these things with ions. In the solid is the same thing. So this thing goes quite big, and this is very common in all kinds of ionic conductors. So this is a family of 7 or materials or so. They all show low frequency polarization. So this is going back to the measurements of the perovskite solar cell. So we have some plateaus. As you know, this means what they are. This is what we need to know. So we have an idea of the possibilities. First thing, in a semiconductor, chemical capacitance, okay, related to increasing the density of states in the material. It must be somewhere, but maybe it's small, we cannot see it because it's overlapped by a bigger capacitance, but it must be there because we know there is separation of Fermi levels, etc. Second, the electric polarization. Well, perovskite has a big dielectric constant, so you can have very big dielectric polarization. These things have a very big difference. Chemical capacitance, when you make more material, you will put more electrons, increase the chemical capacitance. On the other hand, the electric polarization is totally different. You remember the textbook of physics, the electric capacitance is separation of positive and negative charge. When you make more separation, the capacitance goes down, okay? So because the electric field is going down, because the distance is larger. So the dependence with thickness is opposite, and this is something very good to see what is going on. Then we can have electropolarization, which is a candidate to explain this big one, and then we can have some other electronic polarization other than bulk chemical capacitance. So one thing we did explore was the possible ferroelectric property of the perovskite, because if it is ferroelectric, it means ferroelectric can get spontaneous polarization in the absence of even applied field. And normally this is giving very, very large dielectric constant. So we measured, this is the way with piezo phase, using AFM, you study the phase of polarization, and this has to be square to show hysteresis due to ferroelectric polarization. So there is some dielectric polarization in the lead-uride perovskite, but it goes away very fast, so that we cannot induce permanent polarization. In bismuth iron oxide, you can polarize it, and this will stay for several days, polarized like that, okay? But in the perovskite, it will rapidly move away. So it seems we don't have a ferroelectric property. So next important result is again done by Germán García Belmonte. And the new thing in this work is that he explored the capacitance down to very low frequency, because this is the thing I showed at the beginning, and we made many configurations but could not understand it. But when you go to the low temperature, you start to move relaxation phenomena, so you change the plateaus, and here emerge some very nice thing, you see. So this is the room temperature, but when you cool down, you have plateau here, okay? And this is moving to the left when you cool more. And now another plateau appears here. So it's 1, 2, 3. Okay, so this will have now important information. And in order to see the first interpretation, the main thing is to explore this capacitance with thickness, because we need to see thickness dependence. As I said before, if we have the electric, it's inversely proportional to thickness. If we have electropolarization, it does not depend on thickness at all. If we have chemical capacitance, it's proportional to thickness. So here are experiments with different thickness, and there's an important conclusion that in the dark, we have here electropolarization independent of thickness, and the middle plateau is dipolar polarization. Okay, so, and the high frequency plateau more difficult to understand still, because we can have a coupling of some bulk capacitance and contact capacitance. But this is already very good information. The low frequency capacitance is attributed to electropolarization, and then we have some dipolar polarization. So now, this has progressed in the last months. This is work done with Nangyu Park, especially by PhD student Hyosung Kim, and she prepared a big collection of perovskite solar cells with different contacts in order to see the difference of hysteresis. And as I said before, if we have planar TiO2, there's a lot of hysteresis. If you have PCBM and PEDOT, this inverted configuration, it's very small hysteresis. So what happens to the capacitance? So Hyosung, she for the first time could identify very big changes of the electrode in relation with the hysteresis. So here you see this we call normal structure. This we call 5 minutes. Thank you. This we call normal structure. This we call inverted. So for the normal, the capacitance is very big, and the hysteresis also. Here, for example, this is dark and this is light. And the inverted structure with much less hysteresis, we see that the capacitance is considerably smaller. So there's shows that we are sure this is electrode polarization. So this is very important evidence that there's a very strong connection between electrode and this hysteresis, and this is something we want to know, because first we want to engineer the contacts so that we don't have these drastic effects that can destroy the performance of the solar cell. So I think this is the end of my talk. So I have one conclusion. I think this clarifies a lot of the hysteresis and summarizes many results observed in the literature. So there are two causes for hysteresis. They point out to important phenomena. One is capacitive current, which is associated to very large low-frequency capacitance. This is a transient effect, and it's irrelevant for the solar cell operation, which is steady-state operation. And second, there is an evolution of pseudo-steady-state curve, and this is not irrelevant, because something is happening to the perovskite solar cell with time that is modifying the contacts. Okay? The capacitance, we have studies on the dark and has been well understood. We have here, you can see that it goes from microfarad to millifarad under light. Millifarad is very big. Okay, so what is that? I do not think this is ionic capacitance. So I think this is ionic capacitance, like electrode polarization. But when you put light, you have 1,000 more, and this cannot be ionic. So somehow the electrons are going there. Okay, so we will see. That will be the next part of the study. For today, I have finished, and I have to thank my group, especially Dr. Germán García Belmonte and all the rest of the people. And just announced we have a small and very nice conference in Barcelona very soon in March, and you are invited. And thank you for your attention. Yeah.
All right, thank you, Professor Besquart, for your very well delivered presentation. If we can have one question from you guys, from the audience. Yes.
Explain us very well, because you have a planar structure with the TiO2, and if you take the inverted configuration, it's practically the same. What you are having is interfaces are different.
Yes.
The perovskite is the same.
Yes.
In one case, we have a huge hysteresis. In another case, we have no hysteresis. So can we blame this hysteresis for the perovskites, or can we blame this hysteresis to the interfaces?
Yes, as I said before, this low frequency capacitance, we are convinced that it explores the contact, okay? And here the contact is very, very, very different, okay? So, for example, in the dark, there is almost, when you have the TiO2, the ions come to the surface, and then you create a big capacitance, which is this one, okay? When you have Fullerene, this does not happen. You don't create these capacitors. Maybe the ions go a little bit inside or whatever, but the structure of the interface is very different. And in the light you can see, you can create some big capacitance in the two, but still we have two orders of magnitude difference. So I think this is very revealing that it's a contact phenomena, this permanent hysteresis. And in fact, this modification must be that you are modifying somehow the barrier for injection. Okay, so this would be the key idea right now.
Okay, thank you.
Okay, any question or suggestion from the female section? All right, thank you again, Professor Besquart, for your presentation.